Hey guys, hope you're doing well. So this is a grade 11 Physical Sciences Paper 1 exam. It was written by some learners in November 2018, 150 marks, 3 hours long. Hope you enjoy this one and learn some valuable information. Two forces, F1 and F2, act on a point. If F1 and F2 act in the same direction, the maximum resultant has a magnitude of 13. So let me draw that out for you. If you have a point and you've got F1, let me draw it as a little box, and then you've got F2, they said that if they act in the same direction, then the resultant is 13 newtons. If the forces act in opposite directions, so if they act in opposite directions, so maybe F1 is like that and F2 is like that, then the resultant is 3. Determine the magnitude of the two forces. So what you do with this question is you just sort of play around with the numbers. So for example, if I take C, okay, so if I take 3 and 10, so let's say that this one's 10 and this one is 3. Then if you add them together, 10 plus 3, because they're both acting to the right, so you can add them together, that'll give us 13. So that looks pretty good, right? But then if you look over here, so we said that this one is 10 and this one is 3. So now because they're acting in opposite directions, you would minus them. So if you had to say 10 minus 3, that would only give you 7, but they said the resultant is 3. So the answer cannot be C. So that's the way we would approach this question. We're just going to try each of them and see which ones work. So now I'm going to try these ones over here. So that's 8 and 5. So we'll put an 8 over here and a 5 over here, 8 over here and 5 over here. So if we say 8 plus 5, because they're acting in the same direction, that'll be 13. And then if we say 8 minus 5, because they're acting in opposite directions, that'll give us 3. So here we're getting the answers that they told us about, and so that would be the correct answer. So the answer is A. A free moving block slides down an inclined plane at a constant velocity. Okay, so we've got this incline and we've got this block. Let me draw a proper incline here. And we've got this block that is moving down. And they're telling us that it's moving down at a constant velocity. So you should know that when something moves at a constant velocity, the acceleration is 0. If something has a constant velocity, it means the speed or the velocity is not changing, so its acceleration is 0. So if you then have F net equals to ma, and a is 0, then you end up with F net is equal to 0. So that means the net force acting on that object is 0. So the answer for this one would be C. Okay, now I'll quickly go through A, B, and D to show you why they are not correct. So the frictional force cannot be 0. The reason is that there are two main forces acting on this object in the horizontal or along the plane. That is the gravity parallel and friction. Okay, now if friction was not there, then the only force acting down the slope would be this one, and then the object will actually accelerate. So that can't happen. Let's see B. The net force acting on the block is in the direction down the slope. That is not correct. The net force is not down the slope. The net force is actually 0, like we said. So there is no net force. And then D. The component of weight parallel to the plane is greater than the frictional force. If this parallel component is bigger than the frictional force, then the object would actually end up accelerating. But when these two are exactly the same, then the object can move with a constant velocity. A trolley is pushed along a horizontal surface with a force of 150 newtons. The trolley experiences 60 newtons of friction. Okay, so this trolley is definitely going in this direction because that's why the friction is going to the left, because friction always goes against the direction of motion. So here they say, okay, so what we need to do here, they say that the net force acting on the trolley. So we need to go work out the net force acting on the trolley. So we're moving in this direction like that, right? So we need to go work out all of the forces in the horizontal direction. So we've already got the 60 Newton. So what we need to do is take this 150 and we need to break it up to see what would the horizontal part be. And to do that, you use trigonometry. So you can make a little triangle over here like this. And we need to try work out. Well, let me draw a nice little triangle for you over here. So we know that this angle is 45, and we know that this is 150 newtons. So we now need to use trigonometry to try find this x component of the 150. So here you could use sin, cos, tan, all of those, but make sure you use the correct one. So this one's going to be a cos, because we're looking for the adjacent, and we already have the hypotenuse. So you can say cos 45 equals to the adjacent over the hypotenuse, and you would find out that the force of x would be 150 multiplied by cos 45, and so that's going to end up becoming 106.07 if you had to round it to 2 decimal places. So this force going to the right is 106.07. So let's see what they say now. The net force acting on the trolley causes the trolley to accelerate. Yes, it would cause it to accelerate because these two numbers are not going to cancel out. So there will be an acceleration. They said that the net force acting on the trolley is equal to the applied force. That is not correct. The net force acting on the trolley is because of this one minus this one. So that's how you'd calculate the net force. You can't just say that it's equal to the applied force. That is not correct. And then number 3, the net force is horizontally forward. Yes, because this number is larger than this number, we can definitely say that the net force is acting to the right and it's horizontally forward because the trolley is moving that way, so that is considered forward. So this one is correct. So number 1 and number 3 are correct, so that answer is C. A man in a lift is moving upwards at a constant speed. Let's quickly draw that out. So we've got a person in the lift. Okay, and the weight of the man is W. So that man, if I had to draw a little free body diagram, that man has got a weight acting on him. According to Newton's third law, the reaction force of the weight. Okay, so Newton's third law, very, very easy. You just switch the words around. So let's have a look at this one. It says, we know that what that is, that's the weight. Now, what is weight? It is the force of gravity. So it's the force of the earth pulling on the man. So force of earth on man. So if you want to work out the Newton reaction force to that, you just switch these words around. So it will be the force of the man on the earth. That's what we're looking for. And there it is over there. The man on the earth. So remember that when we do Newton's third law, you just switch the words around. The optical density of a medium. Okay, so this is from the chapter of refraction. Okay, so what we know basically is that if you have, let's say you've got light traveling from air into water, and then over here I'm going to show you what happens when you go from water into air. So if you're going from air into water, then what happens is you have a normal line. Now water is very dense, so the light is going to slow down, so it's going to bend towards the normal like that. Okay, so this is because water has a very high density. So this is high density. This is very low density. So this has a very high refractive index. And this has a very low refractive index. Okay. Yeah, I don't really need to show you this part over here, I don't think. Let's just see. So the optical density, if the optical density is very high, then then it refracts the light quite a lot. So the optical density of a medium will be high if the refraction is less. No. So that's not true. Let me try explain. If the optical density is high, then there's a lot of refraction. So we say high refraction. Okay? But here they're saying that if the optical density is high, then the refraction is low or less. So that's not correct. This one says that the optical density is a measure of the refracting power. That's actually true. Optical density, which tells you like how dense it is, it also tells you how much refraction it can do. So what I said here was that when it's high density, then it does a high amount of refraction. If it's a low density, then it does very little refraction. So this one is actually correct. So for this one, the answer is B. I'll quickly explain why C and D are not correct. So they're saying that the optical density is less when the light bends towards the normal. That's not true. When the light bends towards the normal, like we see over here, that is because we have a very high density material. If it was a low density, then it would actually bend away from the normal. So it would look more like that, or even more, it would be like that. Okay? But when it's a high density material, it bends towards the normal. And then let's see this last one. The optical density will be high if the light moves faster. No, that's not true. So what I forgot to mention here was that when you have a high density, you have low speed. And when you have a low density material, then you have high speed. So they're saying that the optical density will be high if the light moves faster. That's not correct. If the optical density is high, then the light would move slower. Which one of the following graphs will the gradient represent the refractive index of a material when light passes from air through the material? Okay, and then we can see there's a whole bunch of thetas and sin and all of that. So this is Snell's law, which tells us that if we've got this formula. Okay, now they tell us that we are passing from air into another material. So that means that the first one is air. So that means this part is the air. Now we should know that the n value for air is always equal to 1. That's just a definition. N of air is always equal to 1. So I'm going to change this to a 1, which means I can actually just take it away because that 1 doesn't do anything. Now it says, in which one of the following graphs will the gradient represent the refractive index of the material? So what you should do now is get this by itself, because that's the refractive index. So just get that by itself. The way you would do that is by saying sin theta of I over sin theta of R. Now, what you should remember is that gradient of a line, gradient is always equal to Y over X. That is what gradient is. It's Y over X. So this would be the Y-axis then, and this would be the X-axis. So is there a graph that has y-axis as sin theta I? Yes, it's this one. And then x-axis is sin theta r? Yes, it's this one. So D is the correct answer. Every point on a wave front acts as a point source of spherical secondary waves that move forward. This statement represents... Okay, I'm not going to go into all the details of this, but this is from the chapter on diffraction and all of that, and you should just know from theory that that is Huygens' principle. 3 charges of magnitudes 2, 2, and minus 2 are shown in the sketch below. Which arrow correctly indicates the direction of the net force acting on the minus 2? Right, so what you do here is, this question is all about this one. So what you're going to do is you're first going to start with, well, it doesn't matter which one you start with, but I'm going to start with this one. And I want you to think about, what does this one do to this one? Well, what you should realize is that this one is positive and this one is negative. So they're definitely going to attract. So that means that this minus 2 is going to want to move upwards. Okay? We don't worry about this one moving downwards because the question is all about this one. Then I want you to look at this one now and look at this one. So they're also oppositely charged. So that means they are going to attract. That means that this one is going to want to move to the right. So think about this. What would happen if something moves up and also goes to the right at the same time? If it goes up and it goes to the right at the same time. Well, doesn't that mean it's just going to go like that over there? Because if you go up and to the right, then you're actually just going like that. And so the answer for this one would be A. Which one of the sketches below represents the correct magnetic field around a straight current carrying conductor? So this is the right hand rule. So remember, you take your right hand, as the name suggests, and you pretend, you can use your pen. I'm sure you have a pen lying around you right now, and you just hold the pen in your right hand. And that'll help you to see how your hands must go around the pen, okay? Now, let's start with A, and let's see if that's the correct one. So, you see this little dot over here. If you've watched my videos on the right-hand rule, you would understand that that dot is a way for them to show you that the electricity is coming out of the page. So maybe I want you to hold that right hand in front of you with the pen, the part where the pen has ink, you know, the part that you actually write with, let that point towards you. So right now you should have your right hand pointing towards you. I know you look crazy right now, but you've got your thumb pointing towards you, your right hand is pointing towards you. So as I said, the thumb is pointing towards you, and the ink is pointing towards you. So if you had to pull the pen closer to your forehead, you'd draw all over your face. So don't do that. That would be quite stupid. But what I want you to do now is look at your fingers, the other 4 fingers that you, I hope you have 5 fingers in total. If you don't, I will give this moment of silence. Okay, so you're going to point those fingers towards you, right? And, or that thumb towards you. And I want you to look at those 4 fingers. Are those 4 fingers doing this? Or are those 4 fingers doing this? If you have done it correctly, those 4 fingers should be doing this one over here. So this answer here is not correct because look at the arrow, it's going to the right. Let's move on to B. So I want you to look at this cross now. Now that cross means that if you've watched my videos, you know that that means going away from you. So I want you to hold that pen again in your right hand, but this time the ink is pointing away from you and your thumb is pointing away from you. Okay? So now it looks like you're Harry Potter and you're like about to cast a spell on someone. But if you do that correctly, I want you to look at your 4 fingers. Are your 4 fingers doing this, or are they doing that? If you've done it correctly, your 4 fingers should be doing that, and that is then correct because this arrow is also pointing to the right. And so the answer for this one is B. Which one of the graphs below correctly represents the relationship between potential difference, which is another name for voltage, and current in a non-ohmic conductor or resistor? So in grade 11, we learn about, or grade 10, 11, and 12, we learn about Ohm's law, right? You know, R equals to V over I, or I equals to V over R. That's Ohm's law. Now, Ohm's law only works when you are busy with the ohmic conductor, hence the name ohm. Okay, so it's an ohmic conductor. If you are busy with an ohmic conductor, then what happens is that if you plot a graph of current and voltage, it actually just makes a perfect straight line. So as the current goes up, the voltage goes up, and nothing changes. Okay, but if it is a non-ohmic resistor, then what happens is that if you make the current, so the current is the I. If you make that too high, then a little problem starts happening. What I want you to think about is you've got a wire, and you've got electrons that are flowing in that wire, right? Now, if you make the current very high, then these electrons are going to be flowing very fast. And what happens is that they flow so fast that they start causing the wire actually starts heating up because of so they start heating up because it starts colliding with all of the particles in the wire. And what happens is that because the wire starts heating up and the particles are starting to vibrate faster, the total resistance actually starts to increase. The total resistance begins to go up. And so if you look at this expression over here, I want you to think of this as the y-axis over the x-axis. Now, whenever you have y over x, that is actually the gradient. So what we can say then is that when you have a graph of voltage versus current, the gradient is the resistance. Now, what we just said was that when you make the current go very high, the resistance begins to increase. So what we can say then is that when the current goes very high, the gradient begins to increase. So I draw your attention to this one over here. In the beginning, it looks pretty straight. That looks pretty good. But then as the current begins to increase, look at how this gradient begins to increase like that. And so that is what happens when you have a non-ohmic conductor. So the answer for this one is C. Two forces of magnitude 50 and 80 act on the Cartesian plane in the direction, as shown below. Okay, so let me just draw this a bit better for us. So we've got a force going here to the right. There we go, of 80. We've got a force going up here that's 50, and then this angle is 30 degrees. First question says, give the correct term for the following description. A single vector having the same effect as two or more vectors together. That is called a resultant. Okay, what do I mean by that? So let's say, for example, you've got vector 1, so that's 1, and let's say you've got another one. Now, or let me rather make it a bit better. Let's say you've got a vector going up as 1, and then a vector going to the right as 2. So what I want you to quickly do is think about the following. Let's say you are this little dot. That's you, right? Now, this person is pushing you upwards. So imagine someone's pushing you that way, and then this person, whoopsie, what happened there? This person is pushing you to the right. So if you have someone who's pushing you upwards and also pushing you to the right, in which direction are you going to move? Would you agree with me that you would probably move off in that direction like that? Something like that, right? So this green line over here summarizes the effect of both of these. So you could almost take these two away and just be like, there, that's what's going to happen. So we call this green line the resultant. Why? Because the resultant is a single vector having the same effect as two or more vectors added together. Right, the next question says, calculate the magnitude. Magnitude just means size, so you don't have to give the direction, you just have to give the value of the vertical component of the 50 newtons. Okay, now many learners that I've seen in the past, they often just think, okay, if it says vertical, if they say vertical, then I must just use sin, and if it says horizontal, then I must just use cos. I don't want you guys to get into that type of thinking because you're going to get caught out sometimes. They can catch you out if you think like that because they can put this angle in weird places. For example, sometimes they'll put the angle over here. They'll put like a 30 over there. And then if you had to use your sin and cos the way I just described, you're going to get everything backwards. So what I would have that you guys rather do is always look at each question by itself. Like, don't come up with these generalized rules. Okay, so what we do, so this 50 Newton, right? If we think about that 50 Newton, would you guys agree with me that 50 Newton, you could think of it as having some part going to the left, and then it also has some part going upwards, right? And those two parts together is what causes the 50 Newtons in that direction over there. So we can actually use trigonometry to take that 50 Newton and we can actually work out the horizontal part and we can actually work out the vertical part. So what we do is we draw ourselves a little triangle like this, and there we have it. So the 50 is the hypotenuse of the triangle. The vertical part is over here, so I'll call this the force in the y direction, and the horizontal part is this one over here, which I'll call the force in the x direction. Okay, you can almost imagine that there's little arrows at the end here. And now it's just trigonometry, you know, using sin, cos, tan. So they want the magnitude of the vertical component. So the vertical component is this one. So we have this 30 degrees, and we're looking for the opposite, and we already have the hypotenuse. So I don't know whether you like to use SOHCAHTOA or whether you use some other weird riddle that your teacher has explained to you. Doesn't really matter. What matters is that you know how to use it. So if you know it quite well, you'll know that this is the opposite, this is the hypotenuse, so we're going to use sin. So you're going to say sin of the angle equals to the opposite, which is called Fy, over the horizontal, which is called 50. And then if you had, or not called 50, it is 50, Kevin. And if you had to go get Fy by itself, you're going to end up with 50 multiplied by sin 30, because the 50 ends up going to the left over there. And so what we end up with now is Fy is equal to 50 multiplied by sin 30, which is 25 newtons. Now technically it would be up, but you don't have to say up, because they just said the magnitude. Okay, so that question is now done. The next one, the magnitude of the resultant. Now, what do they mean by that? Well, this 50 Newton has, this 50 Newton is acting with this 80 Newtons, right? They are both working together. And what those two together are going to do is they are going to cause this object over here to move. We don't know whether that object is going to move upwards and maybe a little bit to the right, or maybe it's going to go downwards and a little bit to the left. We don't know, okay? So what we're going to do now is we're going to try to work out the total result of all of this. Now, you could technically use, well, they did say calculate, but if they didn't say calculate, you could use head to tail, you could use the calculation method, which is the one we're going to use now. So, to be able to calculate the resultant, you need to take this 50 Newton and you need to break it up into its horizontal and its vertical. Okay, that is important. Otherwise, we cannot combine it with this one. So, we already drew our triangle earlier, and we already knew that this one was 25, and that one's going upwards, right? Why is it upwards, Kevin? Why not downwards? Well, guys, look at this arrow. That arrow is going more up, okay? So, it's definitely an upwards force over there, and it's going to the left. Now, what we'll need to do is calculate this force in the x direction. So for that, you would actually have to use cos, because we have the adjacent, well, that's what we're looking for, and we have the hypotenuse. Kevin, can't I just use Pythagoras, bro? Of course you could. We now can use Pythagoras because we have this length and we have this length. But if you just want to use trigonometry, that's fine. Nah, Kevin, I think I'll just use Pythag, my dude. I've been doing that since grade 9. That's fine with me. No worries. Okay, guys, maybe I'm stuck in my office too long, but yeah, I just solidly had a conversation with myself here. Maybe you guys could pray for me. That'll be great. Thank you. So, I'm actually, do I want to use Pythag? It doesn't really matter. Okay, I'm just going to go normal cos 30 equals to the adjacent over the hypotenuse, which is 50. And if you had to go work out the force, you would get 50 multiplied by cos 30. And so that force is going to be, I'm not going to round off because it's not the final answer. So I'm going to leave it as 25 square root 3. And that is definitely going, or it's newtons, and it's definitely going to the left, right? Well, I should probably not say it's just going to the left, right? I mean, like, it's going to the left. You know, so that one's going to the left over there. So let's quickly just fill that in, 25 square root 3. So what we can now do is we can combine these two together, because now they are both acting in the horizontal direction. So we can work out what the total effect of those two would be. So Kevin, should we just add them? Not necessarily. It depends, because you see this one's going left and this one's going right. So you're actually going to minus them, okay? But there's a specific way we're going to do this. So let's work in the horizontal direction now. So we can just work we can say here fx to show that we're working in the x direction. And maybe we can tell them that we would like all the ones going to the right to be positive. You could also say to the left as positive if you want, but I'm going to take right as positive. So that means this one, 80, minus 25 square root 3. So the total forces in the x direction will be 36.6987. I'm going to keep 4 decimals for now, just because it's not the final answer. And that is going to the right. How do I know it's to the right? Well, I chose right as positive, and I've just gotten a positive answer. So that's all good. Now, I need to look in the horizontal direction. So I'm going to do it over here. And I'm going to choose all the forces going upwards as positive. You see, we want to find out what is the result in the horizontal and what is the result in the vertical, and then we can combine everything at the end. So if you look carefully, the only force acting up and down would be this 25 Newton, which is acting up. So we can say that would be 25 Newtons up. So there we have it. We now have all of the totals. We've got this. And we've got this. So now what we can do is, let me quickly show you guys something. So we know now that from both of these forces, the object is going to move to the right. Kevin, how can you tell that it's going to move to the right? What about this one? Guys, we've already taken that one into account. Remember, we've just gone and calculated all of the rights and the lefts, and what we found was that the right was stronger. Okay, so we know that it's going to go right, and we know that that force was that. Then is it going to move up or down? Well, we found out that it's going to move up. So we can draw a little arrow going up, and that's 25. Then we can now use Pythagoras to find out what is the result. So we just use Pythagoras. So we can say here f resultant to the power of 2 is going to be, or let's just go straight for Pythagoras. So it's square root, because in Pythagoras you use square root. And we can say 36.6987 squared plus 25 squared. And if we work this out, we get 44.4 newtons. Now, I know on the memo they got 44.1, but the memos do allow, there's like a range that they give on the memo, okay? And that's just because of rounding and stuff like that. So I went and looked on the memo just to check why the answers are a little bit different. And it's over here where they got 25, where we said 25 square root 3, they rounded to 2 decimals already. So it's really okay. I promise you they're not going to mark you wrong there. Okay, so there we go, that one's fine. And then it says the direction of the resultant force. So that's easy. We just come back to this little part over here, and we actually just going to go work out this angle. Okay, because that gives us the direction. So we could you'll see that your teacher will typically use tan. Why is it that they use tan? Well, it's usually because if we use this angle, we have the opposite side, we have the opposite, and we have the adjacent. So we have opposite and adjacent, which is tan. So we could say tan theta is equal to the opposite over the adjacent, which is that. And then you must say, if you want to get theta, then you're going to have to say tan -1 of that. So you're going to have to say shift tan on your calculator. And so I get 34.26 degrees. Now, let me explain something really interesting. And I wish teachers would make mention of this. You see on the memo here, we have 2 answers. You don't have to get both, you just need to get one. So some of you watching this, I know for a fact you got this as your answer. But then others of you got this one. Any one of them is correct, but let me explain how you can get different answers. You know, earlier when I drew this little triangle, I said that the object is going to go right, and then the object is going to go up. But some of you who are watching this, and it really doesn't matter, you are correct. You might have said first that the object goes up, and then it goes to the right. And then when you connected it, you would be calculating this little angle. You see that? Whereas my triangle was like this. And I was calculating that angle. So together, these 2 angles do make 90 degrees. And if you had to go add these up, they do get 90 degrees. So when I'm getting this as my answer, you might be getting this angle here, which is that one over there. Okay? Now, I also want to teach you how to give the direction in a proper way. So don't just give the angle. What you can actually do is if you get this answer of 34.26, right? Then I want you to look at this and think about this carefully. So we know that this is going to the right. So that's, now some teachers do this differently. Some teachers use north, south, east, and west. Some teachers say positive x-axis, negative x-axis. So please bear with me and just try to use your own, try to remember what your teacher did. So I'm going to call this, because it's going to the right, I'm going to call it the positive x-axis, okay? Because we know with the x and y, x is on the horizontal, and if you go right, it's positive x-axis. And then, okay, so then what I want us to do is, did we go above the positive x-axis, or did we go below the positive x-axis? Well, we went above, right? Because that's why this arrow is going upwards. So what we can say is, you can say above the positive x-axis. For those of you who maybe have teachers who prefer using east, south, north, west, and all of that, then you could say that this is the east line, and we went above that. So you could say north of east. Okay, but now what about the learners who didn't get 34.26, but they rather got 55.74? Well, you guys also, there's also something we can say for you guys. So for you guys, instead of your triangle going right and then up, like what I had, what your triangle looks like is it first goes up, then goes to the right. And so you guys would have calculated this angle, and you would have calculated it as 55.74. So let me just do the result in red. Okay, so that's the result. Okay, so what you guys could say is, you could say 55.74, then we're moving relative to this line, right? Because that line is going up, and we are moving to the right of that line. So you could say right of the positive y-axis, because this is the y-axis and it's the positive one. If it was going down, then it's the negative y-axis. If you have a teacher who uses north, south, east, and west, you could say east of north. What that means is you're going east, which means to the right, of the north axis, which is the axis that goes up. Okay, so I hope that that helps, and I hope that I've answered everyone's questions on how to answer that part over there. The first thing I want to quickly mention is that these are the 6 questions that we are going to do, but I will split them up onto different pages just to give us more space. So here we'll do 3.1 to 3.4, and then there's 3.5 and 3.6. So it tells us that a box with a mass of 45 kilograms is pulled with a force of 90 newtons at an angle of 50 to the horizontal. This next part's important. The box moves at a constant velocity. When you see constant velocity, I want you to remember the following. It means that the acceleration of the box is equal to 0. So if you use something like F net equals to ma, the a is a 0, okay? Because, yeah, when you're moving at a constant velocity, your object is not accelerating. Your speed or your velocity is not changing, so there's no acceleration. Okay, so the first question, quite a boring one. Definitions are so boring. Define the term kinetic frictional force. Okay, so before we get into the proper definition, let's quickly talk about the 2 main types of friction that we know about, static and kinetic. Now, I'm not going to complicate this. Static is when the object is, it's friction when the object is not moving. Okay? And then kinetic is friction when object is moving. Okay, that's not the definition, like the proper answer. We'll get that now, but I hope that that makes sense. And so there's the formal definition. It is the force that opposes the motion of a moving object, because it's kinetic, relative to a surface. So it's the force that it's the force that opposes the motion of an object that is moving on the surface. Okay? Next one, state, another definition. Seriously, state Newton's first law of motion in words. Okay, so before we go into the proper definition, I first want to explain it to you guys. So, what Newton's first law tells us, so let's say Newton 1. What Newton 1 says is that if you have an object, and let's say you've got forces that are acting on that object, the one is 10 newtons, and the other one is 10 newtons. Then what Newton's first law tells us is that the object won't move. The object won't move, okay? Because the 10 Newton balances out, and so the object wouldn't move. And let's say there was like a little table over here. But, if the object was already moving, then it will continue to move, but it will continue to move at a constant velocity. If the object is already moving, then it will continue at a constant velocity. Okay, so yeah, hope that that makes sense. So now let's go get the proper definition of it. So here we have the proper definition. It says that a body will remain in its state of rest or motion. So let me go through it slowly. It will remain in its state of rest. So we said that if it's not moving, then it will stay like that. Or it will continue to move at a constant velocity. if it was already moving, unless there is a non-zero net force acting on it. So if there is a non-zero net force, then the object will start to change its speed or whatever. But if there is no net force acting on the object, then it will continue to remain at rest. Okay. What does it mean when they say a non-zero net force? Well, let me show you what net force is. So if we have 10, and then we have 10 going this way, then what would your net force be? Well, now your net force would be 0. But if you have a 11 Newton, and then you have a 10 Newton going that way, well, then you do have a net force, and that net force would be equal to 1. Calculate the magnitude of the horizontal component of the applied force. So you see this 90 Newton, that is the applied force. But that 90 Newton is in this direction as they're showing with that arrow. Now, what we should know with these types of questions is that this 90 Newton force can be broken up into its components. So if we're to draw a triangle like that, then what we can do is we can take this arrow, which is in that direction as they're showing, and we can break it up into a right and an up. Okay? Because if you make a right and you make a up, then that is how you can make this type of force. So what I'm trying to say is that this 90 Newton can be broken up into a horizontal component and into a vertical component. And we use trigonometry to do that. So here they are asking us for the horizontal. So we're going to make a little triangle where this would be 90. Then we've got this, and we've got this, and then we've got this as 50 degrees. So now you just got to use your grade 10 trigonometry, like sin, cos, tan. And, okay, so if we use this 50-degree angle, and we're looking for this length, because that's the horizontal, and we already have this one, which is the hypotenuse, then we should be using cos. So we can then say that the cos of the angle, which is 50 degrees, is equal to the horizontal, which I'll call fx, which is force in the x direction, over 90. And then to get the fx by itself, you're going to say 90 multiplied by cos 50. And if you had to work that out, you get 57,85 newtons. Now, I'm not going to say to the right. Why? Because I don't feel like it, guys. I'm having a midlife crisis right now, and I'm rebelling against the system. No, I'm just joking. Guys, it just said that we need to calculate the magnitude. When you calculate the magnitude, it means that you don't need to give the direction. You only have to give the size. Okay, so question 3.4. Calculate the magnitude of the normal force. Now, I can tell you from experience that probably 40 to 50% of learners watching this video right now will get this question wrong, and they'll also wonder why it was worth 4 marks. So if that is you, I see you. I know. It happens. Okay? Learners get this wrong all the time. Why? It's because of the way that they show us in class. When your teacher showed you how to do normal force, what they did was they drew a little object. Let's say the object was 10 kilograms. They told you that this object has gravity, which it does. Of course it does. So it's got gravity, right? And then they said that there's this force that goes upwards, and that force is called the normal force. And they showed you so many examples like that. And what that eventually did in your mind is it almost made you think that the normal force is always the same as gravity. So for those 40 to 50% of learners who got this wrong, what you guys would have done is you would have said, oh, normal force, easy, 45 multiplied by 9.8. And that would have been your answer, right? You would have gotten 441. That's not correct, though, okay? The reason it's not correct is because we have this force over here, which is at an angle. You see, what happens is that if I had a little force going to the right, that wouldn't get in the way of these two. So then you would have been correct. But as soon as I have a force that is at an angle, then what we must realize is that this force has a horizontal component, which doesn't do anything to the normal force, but it also has a vertical component. And that vertical component starts to influence these values, or this normal force value. It starts getting involved. And this is where learners get it wrong. And it's not your fault. I'm not going to blame the teachers. I'm not going to be that guy. But I think teachers need to show learners what normal force is, but then also show them that when there's an angle, and then they need to spend a lot of time on that. Okay, so let me show you what we can do. So if we draw a little dot to represent this object, it's a free body diagram. Let's quickly look at all the forces. So there's obviously a vertical, right? So that's your gravity. You can call it W if you wanted to. Then there is a horizontal force, right? Kevin, I don't see the horizontal. Guys, I'm just not pretending. I'm saying that this one's broken up. I like to always show the component. So I'll say that that is the applied force in the x direction. Then I also know that that one has a applied force in the y direction, right? Because that's what we said just now. We said that this force can have a horizontal and it can have a vertical. Yep. Now, it also has a normal force, so I can quickly draw that in. Hate having to draw two arrows like that. It feels so awkward. Normal force. And then we also know that there is friction. Okay, and then I'm just going to show the friction going to the left like that. Okay, so guys, you know when you do normal force is it's a vertical type of force, right? Normal force doesn't go in this direction. So what I'm saying is for normal force, you can ignore those two. But you have to include, now normally, if we just had a box and there was just a gravity and a normal force, and maybe there was some type of applied force, then can you see that the only forces in the vertical would be the normal force and the gravity? So it would normally only be those two. And that's the one that most teachers spend too much time showing, but they forget to show this one where there's an angle. Because now all of a sudden, we've got this force that is also getting involved. So I have a quick question for you guys. Do you think this box is going to like lift off the ground or go into the ground? Or is it only moving horizontally? Well, obviously it's only, in most of these questions, this box is only moving horizontally. So what that means then is that all of the forces acting upwards must be the same as all of the forces acting downwards. If that is not true, then the box would literally go through the ground or it would start floating away. Okay, so what I can say is I can say that these two forces added together must be the same as gravity. So I can say that the gravity must be the same as the normal force added to the y component of the applied force. Hope that makes sense. If it doesn't, quickly rewind. Make sure that that part there makes sense. The gravity must be the same. Okay, you can see the downwards forces must be the same as the upwards forces. Now, all of a sudden, things become quite easy because I can calculate this. We know how to do that. I can calculate that, and then I can get the normal force. So to get gravity, that's quite a complicated one. No, that was just a joke. This is probably a bad joke in case you're tests tomorrow and you're stressed. I'm sorry, that was not good. Gravity in this case, it's not on a slope, so we just use mg, right? So we just use mg. Normal force is just it's what we're trying to calculate. Now to get the y component, you come back to this little triangle over here, and now we're looking for the y component. Okay, keep in mind we do have the 57.85 that we calculated earlier. So if you wanted to, you may use Pythagoras. You can. It's absolutely fine. But I'm gonna pretend like I don't know what that is, and I'm just gonna use trigonometry again. This time around, I'd have to use sin because now I'm using this angle. I'm looking for that one, and I have the hypotenuse. So that's sin. So I'll say sin 50 equals to the opposite over the hypotenuse, which is 90. And so if I had to work it out, I'm going to end up with 90 multiplied by sin 50. And so the y component would be, I'm not going to round off completely because that's not my final answer. So I'll keep the first 4 decimals. So I'll just go 68.9439, 9439. Okay. And now we just need to get the normal force by itself. So if you had to do that, you should get 372.06 and I should say newtons, of course. And now I don't need to say up because they just said magnitude. All right, so let's move on to the next part now. The next question says, calculate the coefficient of kinetic friction. Sorry, now I see that this answer here was actually meant to be written over there, but I'm sure you guys figured that out. So, okay, so on our formula sheets, there is a formula for kinetic friction. So it goes friction due to kinetic over the normal force. Now, we calculated the normal force in the previous question. That's where we got 372.06. That was our normal force. I'm just going to say N But we haven't yet calculated friction. Now, what I want you to realize was that we did break this 90 up into its horizontal component earlier. And we got 57.85 newtons. And we also drew a free body diagram earlier. So we said that this was the applied force in the x direction, normal force, gravity, friction, and the applied force in the y direction. Now, we now see that in this horizontal direction, dimension, we're going to have to look at friction and applied force in the x direction. Okay, now we don't need to look in this direction. So we can use F net equals to ma, because I mean it's 4 marks, so we've got to write out the formula, and we can choose a direction as positive. So let's say to the right is positive. So what forces would we look at? Well, you'd only look at these two over here. So you'd say the applied force in the x direction minus the force of friction. Why? Why did I say minus? Well, because it's acting to the left, and I said all of the forces to the right are positive. Then I'm going to make that equal to 45 times 0. Remember, we said that when the object moves at a constant velocity, the acceleration is 0. So now I can go fill in all of this. So 57.85 minus the friction force equals to 0. If you then had to go calculate the friction force, you would get 57.85. I should say newtons. Okay. Now I can substitute the values into here. So we can use the coefficient equals to 57.85 divided by the normal force from earlier, which was 372.06. And we get, if you round off to 2 decimal places, 0.16. Please note, coefficients have no units. So that is all that you say. Okay. Last question, will the coefficient change if the angle is decreased? Write only yes or no. Okay, so let's have a look. The answer is definitely no. Okay, I'll explain why. So, and I'll also show you the mathematics for those of you that are like really into that type of thing, and you get like 99% for science, and you just really want to understand how it doesn't get affected, okay? So, that coefficient, that value, they often give that value in like textbooks, not textbooks like that you guys use, but like engineering textbooks and stuff and science textbooks. They have all these different values, and it'll often say something like wood and ice. And what they mean is like if you had to take a piece of wood and slide it across ice, and then they'll give you the value of the coefficient. It'll be like 0.12, for example. And then they'll have something like cement and rubber. And then they'll give you a value, for example. So that value only depends on the surfaces that we are busy with and the material of the object. It has nothing to do with the mass. It has nothing to do with the forces involved. Nothing like that. Okay? So we'll say no. We'll say no. And then we'll say that the coefficient only depends on object material and surface material. Okay, now for those of you that, so for most of you, if you're happy with that, you can move on to the next video or whatever. Like that's all that they wanted you to say in the memo. They don't need you to explain the mathematics. But then there's some of you who are probably like, yeah, but I still didn't understand it, and I want to know why. Well, for those of you, I'm going to quickly explain it, okay? But for the rest of you, I'll see you in the next one. Right, so for those of you that are now watching, you are the ones who are interested in knowing how it affects the mathematics. Okay, so we know that the coefficient is a ratio between your friction and your normal force. So what I'm going to go do is I'm going to go look at each of these, and we're going to try to see what happens, okay? Okay, so if I had to decrease that angle, so let's say I decreased that angle to, I don't know, maybe let's say we decreased it, so it's still 90 newtons, but let's say it's now 30 degrees. If you had to now go work out your horizontal force, you would see that it does become larger than what it was. It would become 77.94. Okay, so 77.94. And so because that horizontal force is the same as the frictional force, remember we showed that just now, we can definitely say that this kinetic friction is going to increase. This number is going to increase. We can definitely say that. So Fk will increase if they have to decrease the angle, which is what they said. Okay, now let's go have a look at the whole normal force thing. So if they decrease the angle to 30 degrees, like we said, then this vertical component will actually become a lot less. We can go work it out if you want. It would become 45. Whereas earlier it was like 68 or something. Okay, so that this part here becomes less. So if we then had to go look at that formula earlier where we said that the gravity force is equal to the normal force plus the applied force in the y direction, if you then had to get the normal force by itself, it would be gravity minus the y component of that force. Now, if this force stays the same, this now becomes less, because I just showed you that it would become less, then that means this would become larger. So this normal force would become larger than it originally was. So this is also going to go up. So if both of these are going up, then when you divide them, it has the same, it's almost going to cancel out the effect. I'll prove it to you. If you divide 20 by 5, or if you divide, let's increase this one, let's double that one, and then let's also double this one, you're going to get the same answer. 20 divided by 5 is 4, 40 divided by 10 is 4. So when you're increasing both, somehow it increases by the same order of magnitude. So the coefficient is going to remain exactly the same, no matter what we do at that angle. So remember that that coefficient is affected by the material of the object and the surface material. Here are all the questions that we're going to do for this question. So there's 4 of them, but I'm going to split them up over different pages just so we can make this graph a little bit bigger. So this will be 4.1 and 4.2, and then 4.3 and 4.4. All right, so here we have learners who investigate the relationship between the mass of an object and the acceleration it experiences when a constant net force is applied. Okay, so this is a classic type of experiment that you might have done with your teachers at school, where you have like a little object with a little rope, and then they add mass, and then you work out the acceleration and the net force and the mass and all of that bloody blah stuff. So okay, so they use their results to draw the graph below. Okay, so it's always a good idea just to look at the axes. So we've got mass on the x-axis and then 1 over a on the y-axis. Okay, the first question says, state Newton's second law of motion in words. So we know that Newton's second law in terms of equation is F net equals to ma. That's not the definition, but that's just the formula. So we know that Newton's second law tells us that if there is this is what I'm trying to say, is that this is Newton's second law in terms of an equation, but the actual definition goes like this. So there's the formal definition. When a net force acts on an object, the object will accelerate in the direction of the force. The acceleration is directly proportional to the net force and inversely proportional to the mass. So Newton's second law is actually not this one exactly. It's actually when you get the A by itself. So if you had to get the A by itself, then you would have F net at the top and M at the bottom, so mass at the bottom. So what we can say is that the A and the F net, they both at the top. So we can say that the acceleration is directly proportional to the net force. And then the A and the M, can you see that the A is at the top but the M's at the bottom? That is called inversely proportional. So we're saying that the acceleration is inversely proportional to the mass. So that's literally Newton's second law summarized in an equation. Okay. Right, so we've done that question. The next one says calculate the gradient of the graph. So what you're going to do, you know the gradient formula where you take like y2 minus y1 over x2 minus x1. So you need to do that, right? So you can choose any one of these points on this graph. It can be anywhere on this line, or even these little black dots, because they are literally on the line. So let's zoom in together and we can maybe choose some points. Now I'll give you some advice. Because it's going through 0, 0, I would choose that as a point. It just makes the math so easy. So we choose that as one of our points, and then let's maybe choose this one. So let's zoom in together. Okay, so you got to get this right now. So, okay, I can't really draw when I'm zoomed in, but you got to make sure that you understand how much each of these little lines represents. So, unfortunately, I can't zoom in and write. So, if I had to look at that value, well, let's first try to work out what each line represents. Okay, so you might have to take a bit of time just to get this right, but it looks like every 2 lines is 0.1, so that would be 1.6. Then the next 2 lines would be 1.7. Then the next 2 lines would be 1.8. Then the next 2 lines would be 1.9, and then it goes to 2. Okay, so every 2 lines is like a 0.1. So if we had to look at this one, it would be it's quite tricky, but if you guys had this exam paper in front of you, then it's a lot easier. So that would be 1.6 over there. Okay, so it's 1.7. So the y value here is 1.7. And then the x value, so to read off the x value now, we'd have to look down here. So you got to make sure that you get the whole x-axis correct now. So if you look at it carefully, if you go 0.75, well, let me zoom in quickly. So you see how we have 0.75. Then if you had to skip 2 lines, then it would be 0.8. Then you would skip another 2 lines, and that would be 0.85. Skip another 2 lines, 0.9. Skip another 2 lines, 0.95. And then 1. Okay, so if we had to come down from here, it would be there. Wait, this is so difficult. About there. Oh, no. Let's try that again. So it would be 2 lines, that's 0.8. And then another 2 lines, that's 0.85. So you might have to take your time and just make sure that that makes sense, but it's 0.85. So the x value there is 0.85, and then the y value is 1.7. So now we just go use, and then this point here we said was 0 and 0. So now we can go use the formula. So that's going to be equal to 1.7 minus 0 over 0.85 minus 0. And if we had to work that out, oh, we end up with a lovely value of 2. So the gradient of the graph is 2. Okay, so let's just remember that the gradient is equal to 2. Then they say, hence, determine the net force. Okay, so we need to go back to Newton's second law, which is F net equals to ma. And we somehow need to get 1 over a by itself as the y value, because this is your y, and then get this as the x. So I know that sounds a bit weird what I just said, but what I mean is the following. If we divide by a, then we'll get f net over a. Okay, then what we do is we divide by f net, so you'll end up getting that. And then this would disappear, so that would be a 1. So there we have 1 over a, which is excellent. That's what we have over there. And then we've got the m over here, which is your x-axis. So we almost have like a straight line now. Y equals to mx plus c. We just don't have the c part because it's going through the origin. Okay. Now, remember that the m part, which, okay, now this m and this m are not the same thing. That's going to be a bit confusing. But if you look here, this is the y-axis, this is the x-axis. So this is our y-axis, and this is our x-axis. The thing that is next to the x-axis is the gradient. So that would mean that's the gradient, and it would mean that the 1 over f net would be the gradient of that one. So we have 1 over a equals to, you can think of this as 1 over f net multiplied by m. So once again, this is the y-axis, this is the x-axis. So this is the y-axis, you can see it's over there, and this is the x-axis, you can see it over there. Then the other thing is the gradient. So m is the gradient, so that means this is the gradient. So we can say that 1 over f net is the gradient, but we already worked that out as 2. And so now we can go and multiply this f net over to the other side, like that, and then we can get the f net by itself as 1 over 2, and so that would be the net force. We could say the net force is 1 over 2, or you could say a half, and then that would obviously be measured in newtons. Then it says, write down a conclusion for this experiment. So what you could say here is the following. So whenever you have a straight line going through the origin like that, we call that directly proportional. So we can say is directly proportional to. Then what you do is you just fill in the y-axis. So we can say, and now this is 1 over a, so that's called inverse of acceleration. So we can say that the inverse of acceleration, okay, I'm not going to fill that in, but so say the inverse of acceleration is directly proportional to the, and then the x-axis, which is the mass of the object. So I want to just remind you guys again, if you have a straight line, then this is the y-axis, this is the x-axis. So you can say that whatever the y-axis is directly proportional and then to the x-axis. That is like a constant thing that you can always use for those types of questions. So here I just said that it's the inverse of acceleration because it's 1 over a, and then directly proportional to the mass of the object. Here are all the questions that we are going to do. So it's 5.1 up to 5.4, but I'm going to split them up as to 5.1 and 5.2, and then 5.3 and 5.4, just so we have a bit more space. So here we have a crate with a mass of 25 kilograms. Oh, by the way, I want to share a quick silly story with you guys. This is actually the second time I'm recording this video today. What happened was I recorded this video, and then I started recording a different question after this one. But I forgot to save the recording, and this actually often happens when I'm busy recording. And you know, in life, when this happens, you sometimes want to get so annoyed because like it's a waste of time and you have to start again. But you know what? I've learned and I've taught myself. In that moment when that happens, I tell myself, Kevin, look, you can either act like an average person right now and just get upset and just stop recording for the day and give up, or you can actually just forget about it, accept that you made a silly little mistake, and just get back into it straight away. And when you do that, you minimize the time that you waste complaining about how you've wasted so much time. You accept it, you quickly get back into it, and you just keep going. All right? So I hope that that little story is applicable to some of you watching this, and you can apply it to your own life. If something doesn't go your way, just quickly accept it, get back up, and just keep going as quickly as possible. That is success. Success is not the person who just complains and they're like, oh, I'll just do it tomorrow because now it's all messed up. Okay, so you get up and you just keep going. All right, so with that aside, let's do this one. So it says that we have a crate with a mass of 25 kilograms sliding down a plane which is inclined at 15 degrees to the horizontal. During the first part of the motion, which is from A to B, there is no friction. Okay, so let's make a little note of that. There is no friction over there. No friction. And okay, then it says there is no friction. Okay, but part BC has a rough surface. So that is their indirect way of saying that there is friction for BC. Okay? So here we can say there is friction. There we go. First question. Draw a free body diagram of all of the forces acting on the crate while it goes from B to C. Now, there is this theory going around amongst learners in South Africa, and this theory is really good and it is correct. What they say is that if you look at the mark allocation for a free body diagram, it can help you to see if you've added in all of the forces. So if it's for 3 marks, then there should be 3 forces on your free body diagram. However, if you use FG perpendicular, so that should be FG perpendicular and FG parallel, they count as one force. They count as one force on the free body diagram. Okay, so I'll show you the 2 different ways that you could do this. I like to use FG parallel and FG perpendicular. So let me show you how that would look. So you would have your normal force, which always goes at 90 degrees to the surface. Then you would have your gravity perpendicular, which is at 90 degrees to the surface as well. Then you would have friction, because this section there is friction, and then there would be Fg parallel. So that there counts as one force when you're trying to see if there should be three. So that's 1, 2, and 3. So that works. If you are a student that doesn't like to use Fg parallel and Fg perpendicular on your free body diagram, then you would rather do this. You would do Fg going down and normal force going up, and then Fg, no, Kevin, there would be a friction force like that. So that is what you guys would have. So there we have 1, 2, 3. Okay, so the main thing I want to tell you is that that theory that students have about this being a good indicator, it is good. But if you do Fg perpendicular, oh, I said that very weird, Fg perpendicular and Fg parallel, you count that as one force. Okay, for the 3 marks, if you're trying to see that. Right, now if you've watched my videos, you know that I like to use this one. So if you don't mind, I'm going to scratch this one out for all future questions, but you can use it. It's definitely fine. Right, the first question, or the first calculation question says, calculate the magnitude of the acceleration while it moves from A to B. Now this can confuse learners, because in the first one, they asked us for a free body diagram for B to C. Now they're asking us for A to B. So we have to modify the free body diagram by taking away the friction, because in AB there is no friction. Okay, so we're going to go use the good old F net equals to MA. Choose down the slope as positive. You don't have to, but that would probably be the better option for this one. So the only forces in the downwards direction, or upwards and downwards along that direction, is only Fg parallel. So that is literally the only force we are going to use. I'm not sure if you guys just heard a little timer going off in the background. Maybe you did, maybe you didn't. If you want to know what it was, I've got chicken in the oven and I need to go turn the chicken over. So I needed a little timer to tell me when the oven's about to go. Random story. So Fg parallel, but it's actually funnier than that because it's actually load shedding right now. So the oven switched off. So the chicken's just chilling there, but the oven has switched off. So we have to go out now and go get takeaways or something because... yeah, you know, we didn't know there was going to be load shedding. We have that app that tells you, but sometimes Eskom updates it like suddenly and then you can't like plan ahead. Anyways, hey, I know you guys can relate to this. So we have Fg parallel equals to MA. So we'll just say MA. Now, many learners forget about what Fg parallel is. They always ask me, they're like, sir or Kevin, is it cos or is it sin? Now, you're going to have to just remember this one for yourself, but Fg parallel is the one that says mg sin theta, and then Fg perpendicular, if you ever need to use that, is mg cos theta. So we're going to say mg sin theta equals to ma. Now we just go fill everything in. So we're going to say 25 is the mass, 9.8, and then sin of 15 equals to 25 times A. So if you had to get A by itself now, it would be 25 times 9.8 times sin 15 over 25. And so that would give us 2.54. 2.54 meters per second. So let me put that a bit better. Meters per second. And you don't have to give the direction. That is because they just asked us for the magnitude. Here's the next set of questions for this one. So they now say, write down the direction of the acceleration of the crate while it, now this is the most important part, slows down from B to C. Remember they said that B to C is a rough surface. And so they're telling us that the crate is slowing down. So they want you to write what the direction of the acceleration is. So guys, there are two things that can happen in real life. Okay, or two main things. Let's say you're driving in a car. And let's say your car, you're busy going in that direction over there. Okay, so you're driving to the right. Now, let's say your speed is going 60, 62, 64, 68. So what's happening to your speed? Well, it's increasing, okay? So we will say that you are accelerating to the right. You're going right, your speed is increasing, so you are accelerating to the right. But you can also have a situation where you're in your little car again, going to the right, so you are driving to the right, but then your speed goes 60, 55, 51, 44, 42. So what's happening to your speed? Well, you're slowing down, right? That should be easy for you to understand. If you're driving towards a red robot, you start slowing down, but you're still going towards the robot. So in science, we'll actually say that you are accelerating to the left. Some of you might say, yeah, so that means decelerating and all that. Yeah, we can get into that, but we can also call it accelerating to the left. Okay, so so you can go to the right, you're going to the right, but your object can still accelerate to the left. It doesn't mean you're going left, it just means your object is slowing down. So in this question, we have this box that is over here now, and it's definitely going down the slope. Okay, but they tell us that it's slowing down. So that means the acceleration is actually going to be up the slope. Even though the object is not going up the slope, it can still accelerate up the slope because it's slowing down. Okay, so we are going to say here that the acceleration is up the slope. Next question, 5.4. The magnitude of the net acceleration from B to C is 1.2, but you got to be so careful now with that. Remember that the acceleration is 1.2, but it could be negative depending on what we choose as our direction. They just said the magnitude. Magnitude doesn't tell you left, right, up, down. Magnitude is just the value, okay? So it says calculate the magnitude of the friction force acting on the crate. So we need to go get our free body diagram that we had earlier for the section of B to C. So what we had was we had some gravity. Let's actually draw this over here. We had some gravity parallel. We had some friction. We had normal force. And we had gravity perpendicular. So we're going to use F net equals to MA now. I'm going to choose down the slope as positive. So that means that I'm going to take this one minus this one. You see, we only look in the direction of movement, which is those. We don't look at the normal force and the perpendicular because they're not the direction of motion. So we're going to say FG parallel minus the friction force, because friction is acting up the slope and we chose down the slope as positive. Remember that FG parallel is mg sin theta. Friction is what we're trying to calculate. Now we just go fill everything in. So the mass is 25, gravity is 9.8, slope angle is 15 degrees, the mass is 25. Now here's where you might get caught out. You might say that this is 1.2, but remember we chose down the slope as positive, but the acceleration is acting up the slope. So this would actually be a negative value. If you wanted to put it as a positive, please think about that. Acceleration also has direction. Right, so if we had to now go fill all this in, I'm just going to say 25 times 9.8 times sin 15 minus F equals. Now if you had to multiply these two together, it's negative 30. As I said, there was load shedding. Well, it's still load shedding, so I've got like a little torch light here. So sometimes on my calculator, can barely see. But yeah, it's doable. It's doable. I know a lot of you guys have to study with little torches as well, and yeah, I know it's rough. Hey, it's challenging. So I take my hat off to you guys, being students and having to deal with light issues and Wi-Fi, and I know it's crazy. Okay, so I do feel for you guys, and I do understand. So, but yeah, I'm also sitting here now with a small little torch that's shining like over my laptop and my hand, but it makes shadows everywhere. But anyways, okay, so what we do now is we just try to get this F by itself. So I'm going to take it to the other side, and then I'm going to say 25 times 9.8 times sin 15 plus 30. Okay, and so if we had to then go calculate the friction force, I'm going to write it down here. I'm just going to type all of this on my calculator. We get an answer of 93.41 newtons, and we don't have to say up, down, anything like that, because they just said the magnitude. All right, guys, so that's this question. Here we have a question related to Newton's law of gravity. So here they say that the gravitational force on a probe called Curiosity, they always have these weird stupid names, on the surface of Mars is 3,338 newtons. Okay, so on the surface of Mars, so we're not on Earth here, we're on Mars, and the force of Mars acting on this probe is 3,338 newtons. The radius of Mars is that, and the mass of Mars is that. State Newton's law of universal gravitation in words. Okay, so we know the formula for Newton's law of gravity is on our formula sheet. It's the one that goes like this. Okay, where G is a constant, M1 is the mass of the first object, M2 is the mass of the second object, and R is the radius, or not actually the radius always, it depends. So it's actually, what is this actually? It's the distance between the two objects, right? It's the distance between the two objects. But if you have a planet and you have something like a person on the surface of the planet, then the distance between them is always measured from the center of the planet to the object. So that's also the radius, and that's why they sometimes use a R here, but some textbooks do use a D, because it's actually the distance. So if the object was, for example, up here, then you wouldn't just measure the radius, you would measure all of that. Okay, so keep that in mind. It's actually the distance between the objects, but if it is an object that is on the surface, then it's also the radius. That's why they do that. Okay, so right, now that's not the answer, that's just the formula, but they want the definition. But the definition is often it's easy to remember the definition when you look at the formula. Okay, I'll show you what I mean soon. So here it is, guys. Each particle in the universe attracts every other particle with a gravitational force. Okay, so here's force. Now, anything that's at the top is going to be directly proportional to the force. Anything that's at the bottom is called inversely proportional. So let's check. Directly proportional to the product of their masses. Yep, that makes sense. They're multiplying the masses together. And inversely proportional to the square, because it's got a little square over there, to the distance between their centers. Okay, so you see that the formula often, the definition and the formula are related. Okay, so the next question says, calculate the mass of this little probe. Right, so what we would do here is we would actually just go straight for this formula. And so you would put this in the force, so that would be 3338. The gravitation, G is a constant. If you look here on your formula sheet, you can see there's a capital G there, right? Which is 6.67 times 10 to the negative 11. So that's 6.67 times 10 to the negative 11. The mass of object number 1, now you can choose that to be the probe, or you can choose that to be the mass of the planet, which is the other object. We don't know what. Okay, so that's Mars. Mass of Mars. So I'll let Kevin, get your head together, dude. So what I'm trying to say is that one of these objects is the probe and the other one is the planet. So I just chose the probe as the first one, which we don't know. So then the second object would be Mars, which they've given us the mass of Mars as 6.39 times 10 to the 23. By the way, if it was a question about the Earth, sometimes they'll do that, but then they won't give you the mass and the radius of the Earth. That is because they actually give us that on the formula sheet, and a lot of learners don't know this. You see, if you come look on the formula sheet here, we've got RE, which is radius of Earth, and then we also have M right at the bottom there, which is the mass of Earth. So look out for that in your test or exam. Okay, so what we're going to do now is we are going to go over here. Now be careful, be careful, be careful, be careful. This is measured in kilometers, but when we use this formula, we have to use meters. Now, some of you are like, Kevin, how do we remember that? Like, how do we know if it's meters, kilometers, centimeters, when we use this formula? Now, I've actually got some advice on that. So what you do is you go look at the constant. So let's go to our formula sheet and look at the constant. And then look at that constant G, right? Now look at the units of its constant. Can you see the N, M2, kg? So that means that they're using a M. There's no centimeters there. There's no kilometers there. There's a M. So we have to convert everything to M, which is meters. So 3390, if we had to convert that into meters, well, you would have to multiply that by 1,000. And so that's going to be 339, and then with 4 zeros. Okay, now, so you put that over there. Now, a lot of learners, you forget to put the square. Remember, there's a square there, okay? Now what we need to do is we need to get this by itself. Okay, now there's obviously different ways of how you would like to do that. So I'll show you how I would do it. So I would leave M probe by itself, and then I would take this one down to the bottom. This one would be multiplied up to the top, and then this one would also be divided at the bottom. Whoa, Kevin, that was a bit much, dude. Okay, I know, that was a bit too much at once. So let me show you what I mean. Okay, so we're going to have the 3, 3, 3, 8. We're going to multiply that with the 3, 3, 9, 1, 2, 3, 4 squared. So all I did there was I multiplied that up to the top. Okay, then this part needs to be divided on the left-hand side. So that's going to look like this. Okay, and then this part is also going to be divided on the other side. So it's going to go join this one that's already there. So we can multiply them. You don't have to do it this way, by the way. You can actually do this however you like. Obviously, do it in the correct way, but you know how to do this by now, so you can do it in your own, the steps that you prefer. There we go. Then what I would then go do is I'd now go type all of that on the calculator in one big step. Now, if you do that, you should get a final answer of 900. I get 900.03 kilograms. So that is the mass of this probe over here. So 900.03 kilograms. The next one says calculate the weight, which is mg, of the probe on Earth. Okay, so we know the mass. Some of you might be like, yeah, but Kevin, that's the mass on Mars. Okay, I hear you, but remember that the mass of an object never ever changes, whether it's on Mars or whether it's on the Earth or whether it's on Jupiter. The mass never changes. Okay, it's only the weight that changes because of gravity, but the mass never changes. I mean, imagine if you go to Mars, or let's say you go to the moon, and you get out of your little rocket. Would your arm suddenly disappear? No, everything that you had on Earth is still there, we hope, right? You still have your 2 arms, your 2 legs, so your mass is still there. You feel a bit lighter, but that's just because there's less gravity. So you feel your weight is less, but your mass is still the same. Okay, so mass never ever changes. Right, so we know the mass. We calculated that in the previous question. So now we just need to go Fg, the force of gravity, or the weight. We can just say W if you want. W is equal to mg. And so that's going to be equal to the mass, which was 900.03, because that doesn't change. Now gravity has its own little gravity constant, which is then 9.8. And then we can work that out. And that'll give us 8820.29 newtons. So these are all the 6 questions that we are going to be looking at, but I'm going to be splitting the questions up just so we have a bit more space. So I'm going to be splitting it up onto 7.1 up to 7.3, 7.4, and then 7.5 and 7.6. So here's the beginning. We are told that a glass prism is placed at the bottom of a container filled with water. Okay, so this drawing looks really weird, but what we have is a glass container. Well, actually, I shouldn't say that. It's a container. Let's just say it's a container. Container filled with water. There's the water, okay? Inside that container, we have a little piece of glass. Okay. A light ray passes from the air through the water into the glass. Okay, so this light ray is going to be traveling here in the air, then it's going to go into the water, and then it's eventually going to go into the glass. So this is this question is, it looks like it's targeting the chapter of refraction, Snell's law, all of that stuff. All right. So they tell us that the light ray changes direction every time it passes into a new medium. So if we've watched the chapter on refraction, that shouldn't scare us. We know that when light goes from air to water, for example, the light is going to bend. That is called refraction. So the first question says, name the phenomenon described by the underlying word or the underlined words, and that is called refraction. So we'll say here refraction. diffraction. Next one. If the refractive index, what is the refractive index? That is N, and the formula for N is C over V. Don't get confused with the chemistry formula, which is C equals to N over V. Learners often do get confused with that. So this here is the refractive index, the N, okay? So they say if the refractive index of water and air is 1.33 and 1 respectively, when they say respectively, then that's the order. So for example, they said water first, so that goes with this one. And then they said air, and so that goes with that one. So they then said calculate the angle between the light ray and the surface of the water. See how they're bolding that over there? That is very important. We will look at that just now. If the angle of refraction in the water is 40 degrees. Okay, so this one is interesting. So this type of question will definitely make use of Snell's law, which is this one over here. So let me quickly try to explain what's going on here. They're talking about this part over here where the air goes into the water. So if I do a little drawing for you, here we've got the boundary, here we've got air, and here we've got water. Now we've got the light that is coming in at some angle. Now, okay, so now you got to be, I won't mention too much right now, but okay, so there we've got the light coming in. That's called the incident ray. Then we know that there's always a normal line, so let's quickly draw a normal line. Now we know that when you go from air, which is a low density, and you go into water, which is a higher density, the light is going to bend towards the normal. So it hits the normal like that, and then it's going to bend towards the normal. Okay, that was a bit sharp. It's probably going to go like there. And what we are being asked to calculate, and then you would get a whole bunch of different angles, okay? But I need to give you guys a quick little rundown on this. So let me just draw this a bit bigger. I didn't really achieve what I was trying to achieve right there. Pretty awkward, eh? Are you feeling awkward right now? Yeah, me too. No, I'm just joking. Okay, so let's quickly draw this again. So what you must understand is that they are trying to confuse you on this question. So the angle, it's always the angle between the line and the normal, between the light and the normal. So that's called the incident angle, and the one here is called the refracted angle. That is what we use over here and over here. They're trying to confuse you with this little angle because that is actually this angle here, but we don't use that one, okay? So Kevin, what are we supposed to do? I'm going to show you now, guys. Right. So let's go fill everything in. So we know that this part is the air, so and this part is the I, and this part is the R, and that's water. Okay, so we're just going to go fill in this formula as much as we can. So we know that the N of the I, which is the N of the air, is 1, because they said the refractive index is 1. So we can say 1 multiplied by sin theta of I. Now we don't know what that angle is. We don't know what that angle is at all, so we'll just leave that as it is. Then they said that the N of the R part, which is this, which is the water, is 1.33. So we'll fill that in as 1.33. Then they said, now be careful. This is where a lot of learners are going to make a mistake. They said calculate the angle theta between the light ray and the surface of the water if the angle, that's, this part's pretty cool. If the angle of refraction, so that is theta r, so that's okay. The tricky part isn't coming up just yet. I thought it was there. So that's just going to be sin of 40. Because that is, they said that is the angle of refraction. They're not trying to be funny there, so we'll just put sin 40. Now what we're going to do is we're just going to go calculate sin theta I. And if you had to do that, you should get, because I'm just ignoring this 1 over here, because that's just, 1 times something, doesn't really do anything. Okay, then I'm not going to round off my answer because it's not the final answer, so I'm going to leave 6 decimals like that. And then what I'm going to do is I'm going to say that theta I, then you're going to have to say shift, or you'd probably in an exam you'd say sin -1 of that value, 854,907. So on your calculator you're going to say shift sin, and let's see what we get. And we get 58.75. Now, be careful. What you've just calculated there is theta I, which is this angle over here. But what they're wanting is, if you draw your normal over here, so we've just found this angle, but they want this one. So they're being sneaky. So what we need to do is realize that this is a 90-degree angle now, and we need to now say 90. So we can say that theta is then 90 minus this value that we just found, and that is going to give us 31.25 degrees. So remember, guys, when you use Snell's law, you are using the angle of incidence and the angle of refraction. But what they wanted was none of those. They wanted this angle here. Okay, hope that makes sense. Next one, the angle of refraction in the glass. The angle of refraction in the glass is 35. Calculate the refractive index of glass. Okay, so what they're telling us then is that once this light bends in the water and then it goes into the glass, it's going to refract again, right? It's going to either bend away or it's going to bend towards the normal. Now, they're telling us that the angle of refraction in the glass, okay, so they're giving us the glass's value, and they're telling us that that is 35 degrees. So I definitely want to draw a picture for you guys, just so I can summarize what's happening a little bit bigger. So we had the air, right, earlier on, and we knew what this little angle was over here, and then we said that the light bends like that, and then it's going to travel, and then eventually it's going to hit the glass. Okay, so it's going to now hit the glass. And this was water. Now, if I draw another little normal, what's really cool is that these normal lines are parallel. So we can use alternating angles to find, because if I do this, see, there's an alternating angle there. So it means that this angle is the same as this angle. And we worked this, well, they told us what this angle was just now. That was 40 degrees, remember? So that means that this angle over here is also going to be 40 degrees. So now I can erase all of this stuff. And now we've got a brand new question. But now, because this water, that's now the entering part. So this is now the incident part. And the glass is now the R part. Okay, the first part is always the I, and then the second part is always the R. So we can use Snell's law again, but now this part here is the beginning part, which is now water, and this part is now the last part, which is now the glass. Okay, hope that makes sense. So then what we can do, we know the N value of water. They told us earlier is 1.33. We also know the angle for the water, which was 40 degrees from the previous question. We know that. And then we can go, okay, so we're trying to find the N of the glass. So we don't know what that is, but we do know what the refraction angle is. They said it's 35 degrees. So we can just say sin 35. Now we can just go get this one by itself. So we can say 1.33 multiplied by sin 40 over sin 35. Okay. And so if you had to go calculate that, you should find that the refractive index for the glass will be 1.49. Here's the next one, 7.4. It says, draw the sketch below. Okay, so they gave us this little sketch, and complete the diagram of the path of the light ray from the air to the water to the glass. Show all of the values of the angles of incident, so that's meant to say of incident, angles of refraction, and normal in each medium. All right, so let's start with the normal line. So we can put the normal line over here. Actually, I'm going to make this diagram much bigger. All right, so that's a lot better. So we're going to draw the normal line over here. Okay, then we know that when it goes from air to water, the water has a higher refractive index, so it's definitely going to bend towards the normal. So it's going to go something like that. Then when it hits the boundary of water glass, I need to draw another normal line, like that. Now we need to think about whether it is going to bend away or towards when going into water or between water and glass. So from the previous question, we know that water is 1.33, and we know that glass is 1.49. So we can say N is 1.33, and for this one, it's 1.49. So that means that glass has a higher refractive index. So it's going to go slower in glass. So it's going to bend towards the normal. So it's going to go even more narrow like that. Okay? And then I think we can stop there. We don't have to then go back into the air. So what they're going to be looking for is this angle, this angle, this angle, and that angle over there. So earlier on, we calculated this angle as 31.25. So that means that this angle here is 58.75. That's important. They want that because that's an incident angle. Then they also want us to show this angle here, which was the angle of refraction once it went into the water, which they told us in the previous question was 40 degrees, remember? So we know that that's 40 degrees. So then we know that this is 40 degrees because that's an alternating angle. And then this value here, they also gave us that as 35 degrees. So we can just fill that in as 35. And that's it. That's what they want us to show. Next one, calculate the speed of light through glass if the refractive index of glass is 1.5. Okay, so we here will use the N equals to C over V formula. Let me remind you what each thing means. N is called the refractive index. C is called the speed of light in air, or technically in a vacuum, but we can use it as air. And then V is the speed of light in the specific material that we're talking about. Speed of light in the material. So, we know that in glass, we know the refractive index. We calculated that in this previous question as 1.49. So, we know that, so we can say 1.49. Now, C is a constant that is given to you on your formula sheet as 3 times 10 to the 8. So 3 times 10 to the 8. And then V is what we're looking for. Now, I still see a lot of learners, grade 11s, grade 12s, who struggle to get this by itself. So what you got to do is you got to do two things. You first have to multiply this to the left-hand side. So you end up with 1.49 V. Then you divide. So you say 3 times 10 to the 8 over 1.49. And so if you had to work out V, we should get... Now on the memo, they just say 2 times 10 to the 8. But you can, if you wanted to, you could say 201342281.9 meters per second. Okay? Sometimes the memo just shows it in scientific notation. And they leave out all of this. It's a bit weird. It's a bit of a blurry area. They don't really mention that too much. But I would just leave it like that over there. Okay, then the next question, or the last question, is it possible that total internal reflection of light can occur in the above situation? Write only yes or no. So we know that total internal reflection, I hope you've watched that, the video where I explain that, but total internal reflection can only happen when you move from a high density to a low density. It only works when you go from a high density to a low density. So now we know that the N of air is 1. So here we're going from a low density to a high density. Then for the next part, when we go from water into glass, once again we're going from a lower density to a higher density. Remember that the larger this number, the larger the density. So it is impossible that we could get internal reflection in any of these scenarios, because for total internal reflection to take place, you always have to go from a high density to a lower density. But all of these are going from a low to a high, and then from a lower to a higher. Okay, you got to look at each one. So here we're going from 1 to 1.33. So we're going from low to high. Then for this one, we're going from 1.33 to 1.49. So we're still going from low to high. So to answer that question, we would say no. We don't have to explain. They're only asked for 1 mark. The first thing I want to mention is that these questions do carry on. So on the next slide, We have 8.3 and 8.4, and then lastly we have 8.5. It looks like they're very short questions, no calculations really, just theory, but that's what diffraction is in grade 11, it's just theory. Right, so let me see so what are they saying here? An experiment is performed to investigate the effect of wavelength on the degree of diffraction. Let me stop there. So let's talk about that a little bit. So let's say we have two scenarios, okay? So scenario 1 and scenario 2. In scenario 1, we're going to have a slit width. So let's actually put it over here. And we'll do the same for scenario 2. Okay, and these slit widths are exactly the same. Right, then we're going to have some waves. So these waves are going to be traveling towards the slit width. Getting my tongue twisted here. We're gonna have waves. Now the way that we show waves is by just using these parallel lines like this. Okay, so these are waves that are busy traveling towards the slit. Okay, so these waves are busy going in this direction. You can think of them as like water waves or any type of waves. Maybe it's the waves at the harbor where the boats are, for example, and they're going to go through this little gap. Okay, now that's what the first scenario looks like. In the second scenario, we have this. So what's the main difference? Well, it's literally the fact that the distance, and then let me use a different color to show that that's the boundary. Okay, so this is the boundary between the two scenarios. Okay, so this isn't part of the question. Okay, so what we can see is that here the length between the lines is quite big. Here the length between the lines is quite short. So in this scenario on the left, in scenario 1, we'll say that we have a low wavelength. In scenario 2, we have a high wavelength, or a long, let's rather say long. Let's rather say short and long. That's it, it sounds a bit better. Short and long. Okay, it's literally the distance between the waves. That's why we say short wavelength or long wavelength. That's all we're saying. Nothing complicated there. If the distance between them is very long, then we say long wavelength. And if the distance is very short, we say short wavelength. Now, when you have short wavelength, like here, when it goes through this gap, the amount of diffraction will be very low. So what you would see is that maybe there'll be a little bit of bending, but most of them are actually just going to stay straight. Okay? Right, you won't have to explain why, but you just need to know. In grade 11, this is such a small chapter. So you must just know that when the wavelength is short, the amount of diffraction is very low. On the other hand, if the wavelength is very long, then the bending is actually quite significant. So it actually starts to look like this. See, there's more bending of the waves as it passes through the gap. See that? There's more diffraction. Diffraction is the bending as it goes. It's the spreading out. So with this one, everything almost remains straight, whereas this one, there's a lot more bending and spreading out that we can see. So for this one, we can say, high diffraction. And for this one, we can say low diffraction, low amount of diffraction. Okay, so I hope that makes sense. That's just the summary that you guys need to know for these types of diffraction questions. So the first question says, define the term diffraction. So I'm just going to go get that definition for us quickly. So here's the definition. It is the ability of a wave to spread out in wave fronts. So these are wave fronts, okay? And these ones over here, of course, those are all called wave fronts, as the wave passes through a small aperture or around a sharp edge. Sharp edge, where did I get that from? Sharp edge, okay? Wow. Okay, so next question is, so that was 8.1, that's the definition. 8.2, write an investigative question for this experiment. Now, this is really easy to write down an investigative question. The investigative question could be, just read here, an experiment is performed to investigate the effect of wavelength on the degree of diffraction. So now we just turn that into an answer. We say, how does wavelength affect the degree of diffraction? The degree of diffraction. So I just took their original statement and I just turned that into a question. So how does wavelength affect the degree of diffraction? Okay. Next part says that the degree of diffraction is recorded for different colors. So let's check this out, guys. We know that you get different colors in life. You get the reds, you get oranges, you get yellow, green, blue, indigo, for example, and violet. Okay, it's Roy Gabiv. Now, we know that red is a really chilled, calm color. It looks like this. If red ever had to come past you, it would look like that. Okay, and blue and violet, on the other hand, these are high energy waves. These look more like this. Okay, let me do this a bit better. Okay, so what I'm trying to show you is that your colors like red, they have long wavelengths. See the gaps between the tops? By the way, when I was showing you those, these are all the tops. Okay, those are all the tops. So these are long wavelength. It's got a very long wavelength. But then here we can see the tops are very close to each other. So here we have very short wavelength. Okay, so what I want to show you is that what they're showing us here is that as the wavelength increases, remember what I showed you? As the wavelength increases, what happens to the amount of diffraction? Does it become more or less? Well done if you remember that it becomes more. So that's what they're trying to show us here. As the wavelength increases, then the diffraction, the amount of diffraction or bending also increases. So we've got this proportional relationship happening over here. As wavelength goes up, so does diffraction. So that should make sense. Then it says, write the mathematical relationship between wavelength and the degree of diffraction. So you can say that degree of diffraction, because that's the y-axis, you start with that one, is directly proportional. When it's a straight line like this, it's directly proportional. If it was a graph like this, then you would say inversely proportional. So the degree of diffraction is directly proportional to the wavelength of the wave. Okay, some of you might want to say degree of diffraction. Okay, so that's one way of answering. Here's the second way. Then you can say proportional. I checked on the memo. That's also allowed. And then you can just say wavelength of wave. Okay, so you just need to understand that this is a directly proportional. If it looked like that, then we call it inversely proportional. Then it says here, which color, red or green, has the largest degree of diffraction? Well, if you have been listening to what we've been saying and if you've been understanding, you would know that red has a long wavelength. So it means that it's got a very high diffraction amount. Green is over here. By the way, I've listed all of these in order. So green is over here. So green would have a little bit of a shorter wavelength because it's closer to blue. So green would have a bit of a shorter wavelength, so it would look more like that. Okay? So green has lower wavelength than red. Okay? So remember, the longer the wavelength, the more diffraction. So that means that green would diffract less than red. So it says which color, red or green, has the largest degree of diffraction? That's definitely going to be red because it's got a longer wavelength, and when it has a longer wavelength, then it diffracts more. We looked at that. Last one. The experiment is repeated with only green light with a wavelength of 560 nanometers, but the slit width is changed and the degree of diffraction is recorded. So I want to quickly remind you guys, how does slit width affect degree of diffraction. I've already showed you how wavelength, but I haven't yet showed you slit width. So it's very easy. I'll show you what to do. So let's look at scenario. Let's break it up into two scenarios again. Scenario 1 and scenario 2. So in scenario 1, I'm going to use a huge slit width, like literally like that. In scenario 2, very small slit width. Okay, now imagine you've got these waves arriving. So we're going to keep the distance between the waves the same now. It wouldn't be fair to change two variables at once. Okay, now imagine, look at this, guys. It's so simple. If you take these three waves and you let them go towards this gap, can you see that the gap is so big that the waves are hardly going to bend? They might bend a little bit, like maybe a tiny bit. See, there might be a little bit of bending on the edges, but the rest of the wave, this part in the middle, that's just going to go right through the gap. So there's not going to be a lot of diffraction happening there. However, if you look at these three, there's going to be a lot of diffraction, because as soon as maybe this part here in the middle, that's going to get to the middle, and nothing's really, it's just going to go right through. But the rest of the wave is going to bend a lot, okay? So we're going to get a lot of diffraction. So it's probably going to look like this. Okay, so what we can say then is that if you have a small slit width, then what happens to the amount of diffraction? Well, that's very high. And if you have a large slit width, then the amount of diffraction, which is the amount of bending, is very low. So now it looks like we have an inverse relation. If the slit width is small, the diffraction is high. If the slit width is large, the diffraction is low. So that's an inverse relation. So you draw your inverse graph like that. I know it's tempting to sometimes just want to draw a straight line, but we never do that. If it's inverse, we always make it like a hyperbola, or almost looks like an exponential graph. All right, so I hope that makes sense. So in this video, we've actually learned some really good things. We've learned that the relationship between diffraction and wavelength, as well as diffraction and slit width. That is really all that they could ask you in an exam. There's no calculations in grade 11 about this chapter. It's just a theoretical kind of chapter, and it won't be worth that many marks. So here we have a electrostatics question. We are told that we have a small isolated sphere A with a mass of 0.2 grams. Okay, so this one has a mass of 0.2 grams. Carrying a charge of 7 times 10 to the minus 9 is suspended from a horizontal surface, okay, by a string. A second sphere carrying a charge of blah, 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 on an isolated stand attracts sphere A so that the strings form an angle of 20. The horizontal distance between them is 3 centimeters. Okay, so the first question says, state Coulomb's law in words. So before we get into the definition, I always like to show you guys the formula, because from the formula it can help you to remember the definition, because sometimes you're sitting in an exam and you might hit a blank, but if you write out the formula, it can remind you. So I went and got this from the formula sheet, so there it is. So what I want you to see now is that there is charges that are being multiplied together, so that's called a product. Now, this R is at the bottom, and these two are at the top. So if I want you to look at the F, and I want you to look at everything at the top, everything that's at the, how can I say this? Okay, so when these are at the top and these are at the top, then we call that directly proportional. When this one's at the top and this one's at the bottom, we call that inversely proportional. Now I'm going to go get the definition, and you'll see what I'm talking about. There is a relationship between the definition and the formula. So here we have it. The magnitude of the force, is of the electrostatic force between two charges is directly proportional to the product of the charges, there they are, and inversely proportional to the square, because it's got a square, of the distance between them. Pretty cool, hey? So there's our definition. Next question. Draw a vector diagram of the forces acting on sphere A indicate at least one angle. Okay, now why are they telling us to indicate at least one angle? That sounds scary. I don't know about you, but that sounds weird, eh? Anyways, let's see what we can do. Alright, so when they say vector diagram, by the way, we didn't even pause there. That was pretty awkward, eh? Vector diagram, like what is that? Guys, when they say vector diagram, I don't know. It's pretty random. You don't really see it too much, but you can think of it as free body diagram. Okay, so we'll just do free body diagram. So, force charge A. Now, charge A, they told us, has mass. Anything that has mass would also have gravity acting on it. So that would be our first one we can put there, saying gravity. And then, of course, we've got these two guys over here, so charge A and charge B. They are obviously charges. So the one's positive, the one's negative. If they were both positive, doesn't really matter. The point is when you have two charges, they are going to exert a force on each other. And that's this whole Coulomb's force or electrostatic force. Now, you got to think about it carefully. So we're doing a free body diagram on A. So we want to know what forces are acting on A. So what would B do to A? Well, the one's negative and the one's positive. So they are going to attract. So my question to you is, what is B going to do to A? Well, B is going to pull A to the right. No, but Kevin, A is going to pull B to the left. Yes, that's also correct, but we're not looking at B. We're looking at A. The free body diagram is on A. So we're going to draw an arrow going that way. And we can just say that this is an electrostatic force, just like that. Now, what other forces are there? Well, the only other force is this little arrow. This rope, okay? Now, what is that rope doing? Well, think about it carefully. A rope can't push. Try push someone with a rope and let me know how that goes. It doesn't work, right? A rope can only pull. So it's going to pull in that direction over there. So we can do that. Right. Now we could say that that's a tension force, like that. Now, that would technically be done for a free body diagram, but they did say indicate at least one angle. Now, how are we going to do that? Well, what you don't want to do is go put the 20 over there, because that's not correct. I'll show you what I mean. If we're to if we're to go like this, then this is 20, so then this is 20, just because of alternating angles. So what I can do is I can draw a dotted line going up here. If I could go straight, that would also help. Don't know what's wrong with me today. So I do a dotted line going up like that, and then I could put 20 degrees like that. And there we've done it. They did say show at least one angle, so we've shown at least one angle. Alright, so I've just brought this free body diagram over because we might need to use it now. So it says calculate the magnitude of the electrostatic force that B exerts on A. Okay, no, we don't need anything. We don't need the free body diagram. So this sometimes confuses learners. They're saying calculate the magnitude of the electrostatic force that B exerts on A. Now, because of our good old friend Newton, what he discovered was that in Newton's third law, the force of B on A or A on B is exactly the same. So they're actually just asking you to calculate the force between these two. Now, how do we do that? Well, we just use Coulomb's law, because that is the formula to calculate the force between two charges. And they're saying here, the electrostatic force. So here we have the formula over here, and we also have the value of K. So we can just go fill it in now. So we can just go F equals, now K is a constant given to us on our formula sheet as 9 times 10 to the 9. Q1 would be the charge of 1, which is, we can say that one for example, so that's 7 times 10 to the minus 9. Q2 would be this one, but remember when we use this formula, we don't use the negatives that you see in the front there. We don't use the negatives. We only use the charges themselves. And then the distance, be careful guys, that needs to be in meters. Kevin, how am I supposed to remember what units I'm supposed to use? Good question, but it's quite easy. I'll show you a little trick. What you do is you look at the formula and you look at the constant. Now the constant is K. So then you go to K and you look at all of its units. Look at that. There's a M. See, there's not a centimeter, it's only a M for meter. So that means we're going to use meters. Kevin, how do we get from centimeters to meters? I hear you awkwardly asking me. It's okay, we all forget these things from time to time. So you are just going to divide by 100. So you're going to divide by 100. So that means 3 centimeters will be 0,03 meters. So we'll say 0,03. and then we're going to square that over there. Go ahead, type this all in on your calculator, and you get an answer of 5.6 times 10 to the negative 4, and that would simply be in newtons. And the last question, calculate the magnitude of the tension force in the string. Now this is actually very easy. I'll show you guys the way it works. We know that this object A cannot move, right? We know that it's not moving, so it is in equilibrium. When something is in equilibrium, it means that all of the forces acting to the left must be the same as all of the forces to the right. So all forces acting left must be the same as all forces acting to the right. Okay, it also means that all forces acting up must equal all forces acting down. Okay, that is just basic equilibrium. So what we can do, we already calculated this force over here earlier as 5.6 times 10 to the negative 4. So what we could then do is we could say that this 5.6 times 10 to the negative 4 must be the same as all of the forces going to the left. Now some of you are like, Kevin, there are no forces going to the left. Bro, yeah, I hear you, but remember that this Ft, this tension force, it's got a little bit of a left and it's got a little bit of an up. That's how it goes in this direction. So it's got a little bit of a left and it's got a little bit of an up. So what we'll do is we will break it up into its components, and then we have something to work with. So what I would do here is I would work out this little angle as 70 degrees. That's easy, right? Because that's 90. So if this one's 20, then this one's 70. Okay, then I'm going to put the Ft over here. Now what you do is you use trigonometry. So you could make a little triangle for yourself over here. Okay, and if I had to enlarge that triangle for us a little bit, we've got a horizontal, we've got a vertical, and we've got Ft. And we've got this as 70 degrees. So we use trigonometry like sin, cos, tan. And what we're going to try to do is we're going to try to find this Ft in the x direction. So we are looking for the adjacent, and we have the letter for the hypotenuse. So what we can do, that'll be cos. So we could say that cos 70 is equal to the adjacent over the hypotenuse. Then if we had to get the adjacent by itself, we would end up getting Ft cos 70. So what we can now do is, let's go back to our little free body diagram that we had from earlier. So earlier on we had it as Ft, but now I've broken that Ft up into its horizontal, and then if I wanted to, which I don't, but if I wanted to, if I needed to, I could have also worked out its vertical component like that. So now I can actually say that these two must be equal to each other. Because if it wasn't, then the object would literally start moving left or moving right. But it's not moving, so those two forces must be equal. So what I can say then is that the tension force in the x direction must be the same as the electrostatic force. You can also, if you wanted to, say that this one must be the same as this one. But then you're going to have to go do a few more calculations, and you're going to have to go get the gravitational force, which is not difficult. You can do it that way. And on the memo, they have different ways, and that's why we have different answers. Some of the answers are quite different, which is weird, but hey, it is what it is. So what we can then do is say Ft cos 70. See, because that's what Ftx was, right? That's what we said over here. And we can make that equal to Fe, which we calculated earlier as 5.6 times 10 to the negative 4. Then to get the tension force by itself, I can just say 5.6 times 10 to the negative 4 divided by cos 70, and that's going to give us a tension force of 1.64 times 10 to the negative 3 newtons. And I don't need to give a direction because they just said magnitude. So to get these answers, there's obviously different ways we could have done this question. You could have maybe said that the tension force in the Y must be the same as gravity. That would have also worked, but it might have given you a different answer. So yeah, those are the different options. So there we have it. So here we have an electrostatics question. These are all the questions we're going to be doing, but I'll split them up over different pages. So let's begin. 2 points, P and T, are situated 3 millimeters apart, as we can see in the diagram below. First question says, draw the electric field pattern around Q. Okay, so let me quickly give you a summary of electric patterns. So the lines always go out of positive, and the line... Okay, guys, I'm joking. I'm not going to make a stupid song so you guys can remember this. Wow, that would have been funny. What we're going to do is... positive, you're just going to have to remember that the lines go out of that one. Okay, so lines go away from positive. All right, and then lines go towards negative. That's all that you need to remember. That's it. That's what you got to remember. So for Q is positive. So what you'll do is you'll draw a little charge with a positive, and then you're just going to draw lines going away. Okay, and you can also show some lines there. It doesn't really matter. Okay, so for 10.1, that is what you would do over there. The next one says that the magnitude of the electric field. Okay, so that's E, right? Not F, that's E. Because remember, we get E for questions, or we get things where we have to work at E, which is electric field, and F, which is force. So this one is electric field. At point P is that, and at point T, the magnitude is that. Oh, that's interesting. So they're telling us the P at different places. So for 1 mark, calculate the ratio of the electric field at point P to the electric field at point T. Okay, so what I would do is I'd go electric field at point P divided by electric field at point T, and that would be equal to 4 times 10 to the 6 over 2.5 times 10 to the 5, and if we work that out, we get 16, okay? And so what we can just say then is that EP to ET, so EP is 16 times bigger, so we can just say 16 to 1. Okay, now we're carrying on with 10.2.2, so it says, and remember we just said that the electric field of point P to the electric field of point T was 16 to 1. So it says calculate the distance between Q and P. So this is quite an interesting question. So what I think we can do is we know the fact that the electric field at point P divided by the electric field at point T is 16 over 1. Then we're going to use the electric field formula. Now remember that we've got these two formulas for E. Now what you must remember is that this Q and this Q are two very, very different things. This Q is the charge producing the field. This one is the charge that is experiencing or feeling the field. So what we must understand is that P and T, they are not this one, and they're also not that one. These aren't charges. These are just two random little places. So they are two random little places, and there is an electric field being registered over here, and that would be because of this one, which is producing the electric field. So we cannot use this formula. We have to use this formula over here. So I'm now going to use, let me just quickly erase this. I'm quickly going to use this formula now in there, and I'm also going to use it there. So we're going to say KQ over R squared, but now let's be careful with what the R is. So let's call this X. This little distance here, let's call that X. So from Q to P, the distance would be X. So I can fill in X squared over there. And then for this other one, oh, and remember that, now we've got to be careful. Okay, let's say this is in millimeters. So we know that we have to divide by 1,000 if you want to get it in meters. Okay, because that's in millimeters. And then the next one is now going to be this one over here. So that's going to be kq as well over, now the distance is x plus 3. So x plus 3, because it's from q to t, and that's over, I'm running out of space here, guys. Okay, so that distance is x plus 3, and that's over 1,000 squared. And we know that that should give us 16 over 1. Now, what I'm going to quickly do is just show you what's going to happen with this side over here. So we know that when you have a fraction divided by another fraction, then you can actually just turn it into a multiply and then flip this side upside down. The reason I did that is I just wanted to show you that these kq's are actually just going to cancel out. So we don't even need to know what q is. Of course we know what k is, but don't fill it in if it's going to cancel out. So what I'm now going to do is I'm going to replace this entire part with this. So it's literally just going to be this one at the top and this one at the bottom. So that's what we now have. Okay, and now, without getting too technical, if you have a square on top of a square, and you can do another method if this doesn't feel comfortable to you, like you could use cross multiplication right now, but if you have a square over a square, you can actually just make it as one big thing, and then just put the whole thing in a square. Now, this part here, you could go do that whole flippity flip thing like we did over here, and I'm going to leave that for you to try, but what you would notice is that you are going to end up with the 1,000s cancelling out. So you're actually just going to end up with x plus 3 over x, and that's still to the power of 2. That's still to the power of 2 over there. And some of you are probably like, oh, yes, dude, let's just cancel that stuff out there. But remember, you cannot do that because we have 2 terms at the top and only 1 term at the bottom. So that's from like earlier grades. I know some of you still have those building blocks that are not so good because I know that's how I was in grade 9 and 10, and it affected my grade 11 and 12 where I'd be like, oh, yes, sorted. But then, yeah, it doesn't really work. Okay, so what we're going to do now, you could go multiply those brackets out, you know, because it's squared. But what I'm going to do is I'm going to say square root. So we're going to square root. And yes, for all of you technical learners out there, we should say plus and minus. Okay. And then the square goes away. And so the square root of 16 is 4. So we could say that x plus 3 over x is equal to plus and minus 4. Okay, and so now I'm going to do the first one. So x plus 3 over x equals to positive 4. And if we had to solve that, you could take this x over to the other side. So you'd end up with that. And then you could take this x over. So you end up with 3x equals to 3. And so x is equal to 1. Okay, so there's our first answer. Then we should do the negative one. Negative 4. And then we would take the x over. Now, if you had to carry on solving this one, you are going to get a negative answer. And then you're going to tell them that x cannot be negative. The reason that x cannot be negative is that x is a distance, and you cannot have a negative distance. Okay? So this one's eventually, just because of space, that one's not going to work out. And so the only answer would be 1. And so the answer is 1 millimeter. Kevin, shouldn't the answer be in meters? Guys, remember, we said that x was the millimeter one already, and then we just went and divided it by 1,000 in the calculation. So if you wanted to, you could definitely say 0,001 meters, or like 1 times 10 to the negative 3 meters. That's also fine, okay? And then the last question, this will be an easy one, 2 marks. It says calculate the magnitude of Q. So what we could now do is we could use this formula, the one that we had earlier, and we can just choose either point P or T. You can decide whatever you want. You will get the same answer. So I'm going to choose point P. So we're going to look at Q, which is producing the electric field, and P is the one that is, well, P is the point where we're looking at. So we already know the E value at P. They told us it's that one. So we can say 4 times 10 to the 6 equals to K, which is a constant on your formula sheet of 9 times 10 to the 9. Q, we don't know. Now that would be this Q, remember? Because on this formula, this Q is the one that is producing the electric field. And the distance is 1, but it's has to be converted to meters, like that. Okay, and don't forget that square. So now we're just going to go and get Q by itself. So what I'm going to do is I'm going to multiply this over to the left-hand side. So we're going to end up with this. And then I'm going to divide by this one. And then on the right-hand side, we'd be left with Q. Okay, so we're just going to go plug this all in on the calculators now. And we get 4.44 times 10. I'm running out of space. Sounds like a song. I'm running out of space. Okay, no, that's terrible, Kevin. 4.44 times 10. Maybe I could have been a hit. 4.44 times 10 to the minus 10. Coulombs. Is it coulombs? Are we calculating charge? Yes, we are. Okay, yeah. And there's the answer there as well. Excellent. So that's that question. In this question, we have a square coil. So what that means is that these are the magnets, and then there's a piece of square coil. So I'm going to try to draw this out for you guys. There is like a loop of wire over here in the shape of a square. Okay, it's like in 3 dimensions. So we are only seeing it from the side. But you can imagine that, let me try to draw that again. It looks something like this. Okay, I hope that that makes it a bit clearer for you. And we know that each of the side lengths of the square is 3 centimeters. And we've got 400 windings. And it's placed perpendicularly. So this is perpendicular. We can see it's got 90 degrees in a uniform magnetic field. And it's then rotated. Okay, so we're going to rotate it just now at an angle of 45 degrees. And it's going to take 0.08 seconds. We are then told that the EMF is going to be 7 volts. Question 1. State Faraday's law. Okay, so this is just something that you need to memorize. Now, I know that your teachers probably tell you that you need to know it off by heart, but there are actually many different variations of the definition that you would find. So I'm just going to write out the basic definition, but you must just use whatever your teacher has been using with you. Okay, or use whatever your textbook says, because each textbook is going to change it slightly. Okay, so here's my definition. It says that the induced EMF on a conductor is directly proportional to the rate of change of magnetic flux linked to the coil. So if I show you Faraday's equation, which goes like this, we can see that the EMF is directly proportional to the rate. Now, rate is usually talking about time, so it's and then we've got the change in magnetic flux over here. So when you're dividing by time like that, we call that the rate. So it's directly proportional to the rate of the change in the magnetic flux linked to the coil. Question 11.2, calculate the change in the magnetic flux. For this question, I'm actually going to leave this formula here because we can actually go and use this formula to work this one out. And so we know now that they're looking for change in magnetic flux. And so we can fill in the EMF. They said the EMF is 7, and there's a negative, and then there's 400. That's the number of loops. Then we don't know what that is. And then the time, they said that the time is 0.08 seconds. Remember, you don't have to go expand this into BA cos theta because they're asking you for the change in magnetic flux. And so now you just need to get it all alone. And so we need to get change in magnetic flux alone. And so that would give us 7 multiplied by 0.08 divided by negative 400. And so your change in magnetic flux will be negative 1.4 times 10 to the minus 3. And let me just put that. You don't have to give a direction or anything like that. 10 to the minus 3, and that would be in Weber. The next question says, calculate the magnitude of the magnetic field. So, you know that formula that goes magnetic flux, or let me do this in black for now, and then I will show you the label. So we know that magnetic flux is equal to B A cos theta, where this first one is called magnetic flux. B, that is known as, well, let me write that down here rather. That is known as magnetic field strength. So that pretty much says how strong are the magnets. Magnetic field strength, some teachers will say magnetic field density. That's also perfect. A is the area of the loop. So you know we have like a square loop over here. It would be the area of that. And then theta, very interesting one this, that is the angle, but not just any angle that you see. For example, if you see 45, you're not going to just say, oh, it's 45. It might be, but that's just a coincidence. So it's the angle between the normal line and the magnetic field lines. All right. So they are asking us to calculate the magnitude, which is the size of the magnetic field. So they are actually asking us to calculate how strong is the magnet. So they would like to know what is B. Now we cannot use this formula just like this because we don't know what the magnetic flux is. Some of you might be saying, yes we do, Kevin, we just worked it out, can't you remember? Guys, we didn't work out the magnetic flux, we worked out the change in the magnetic flux. There's a slight difference there. So what we can do is we could use the change in magnetic flux formula, which goes like this. We know that the change in magnetic flux is BA cos theta, and this would be the final condition, because change always means final condition minus initial condition. Now we know that the change was equal to negative 1,4 times 10 to the minus 3. We worked that out in the previous question. Now that's going to be equal to B, which we don't know. Now the area is the area of the loop. Now each side of that square is 3 centimeters. So we know that area is obviously 3 times 3, but it has to be in meters. Now some of you watching this might have said, okay, fine, Kevin, I'll just say 3 times 3, which is 9, and then I'll just divide that by 100 because that's how you go from centimeters to meters. But that is wrong. It's a bit weird, I know, but it's because you are working with area, which is to the power of 2. So my advice, convert the 3 centimeters into meters, which is going to be 0,03 meters, then calculate the area, like that, and that's going to give you 9 times 10 to the negative 4, okay? And so that's the area, 9 times 10 to the negative 4. Or actually, I'm just going to keep it as 0,03 squared. Just makes it easier, less space needed. And now the angle, this is an interesting one. Now they're talking about the final position. So remember that what we can see on our screen right now, that is not the final position, that's the original position. The final position, they said it was rotated by 45 degrees, so it's going to be over here, for example. That's what the loop is going to look like in the final position. And so to work out the angle, remember that the angle is between the normal line. Now a normal line is a 90-degree line to the loop. So a 90-degree line to the loop would look something like that. And so it's the angle between that pink line and the magnetic field lines, which I'll do like that in green, because that's the direction of the magnetic field lines. And so they want to work out the angle is that angle between the normal and between the magnetic field lines. And if you had to go think about this a bit for yourself, you will get to 45 degrees. That's just because 45 is half of 90, and so it works out to be 45. But if this angle was like a 30 or something like that, then you got to be careful, because then the angle you would have used might not be 30, but it might end up being 60, for example. But in this case, 45 is correct. So we'll say cos 45 minus B, and the area in the original position is still the same. Now let's look at the angle from the original scenario. So we know that the magnetic field lines, I'm going to do that in green, so they're going like that. And then a normal is a 90-degree line to the loop, so that would also go like that. So because both of those are in the same direction, the angle is 0 degrees. So you would say here, cos of 0. Right, now,
all of these have a b in them, so we can combine all of this into one term. And so I'm going to say minus 1,4 times 10 to the minus 3 equals 2. Now I'm just going to type all those numbers on the calculator. So that's negative 2,636. I'm not going to round off just yet. Times 10 to the negative 4, b. And now we can get b alone by dividing. And there we get a nice answer of 5.31 Tesla. So that is the strength of the magnetic field, 5,31 Teslas. 11.4. The coil is now rotated 45 degrees in 0.05 seconds. Okay, in the beginning it was rotated 45 degrees, but they did it in 0.08 seconds. So that means that they are now rotating the coil faster because the time is less. So they're rotating it faster. So it says, how will the induced EMF, which is from this formula over here, how will that be affected? Well, logically, most of us probably are comfortable with the idea that the faster you rotate the coil, the higher the EMF that you'll be able to induce. We've spoken about this before, where we found out that if you want to make electricity, you must move the magnets or the coil relative to each other, but you must move them as quickly as possible. Okay? So if you make the time less, we know that it's going to make the EMF larger. So we can say that it will increase. Now for 1 mark, explain your answer. We can just say something like, induced EMF is inversely, remember when this is at the top and this one's at the bottom, it means that when this one gets smaller, this one gets bigger. That's what inverse means. So we can say that induced EMF is inversely proportional to the time. In this question, we have a north part of a magnet that is pushed into a solenoid. Okay, so from our discussions about solenoids, we know that, let's say for example, we have a solenoid over here. Okay, so here's a solenoid and it's got all these loops. Okay, so you've got some type of solenoid like that. Then if you take a magnet, north, south, and let's say you push this magnet towards that solenoid is not going to be very happy about that, and it's going to try to repel that magnet. So what must the solenoid do on this side over here? Should it make a north or should it make a south? It will make a north so that it can try to push this magnet away. So it's going to make a north. The next question says, in which direction will the induced current flow? So we know that when you push the magnet into the solenoid is going to try and make a north on the left-hand side. How does it make a north? By creating its own electricity. It creates its own electricity, and when its own electricity starts to flow, it will produce a magnetic field that will push the solenoid away, or it will try to repel it. So, to work out the direction of the electrical flow in the solenoid, either your fingers are going to wrap around the solenoid like this, or they are going to wrap like that. So how would we know what it's going to do? Well, remember, the right-hand rule of a solenoid tells us that you should hold the solenoid in your right hand and your thumb must point north. So pretend you're holding that solenoid in your right hand and let your thumb point north. So your thumb should be pointing to the left-hand side of your screen right now. And if you look at what your fingers are doing, you should see that on this side of the solenoid, your 4 fingers, should be curling upwards like that. So that means that the electricity is going to flow from A. See how it goes from A, then it goes over, comes back around, and then eventually goes over here, comes out the other side to B. So it's definitely going to be going from A to B.
So here is a electric circuit question. These are all the questions we're going to do. Let's begin. So they say, consider the circuit diagram below. This is important, the internal resistance of the battery and the wires. Okay, well, that's obvious. We always know about that. But the internal resistance of the battery and the wires can be ignored. So that's important. Internal resistance of battery can be ignored. Okay, so no internal resistance. Normally there would be, so that there's none. So it says calculate the value of resistor R if the total resistance of this circuit is 4.8 ohms. Okay, so we know that the electricity flows out of the positive terminal. Now watch what happens. It goes, gets to this point over here, and now it can go in two different paths. It can go this way and it can go this way. As soon as that happens, it means that we are now in a parallel section, because the path is able to decide which way it wants to go. Okay, so let's say that the main part was here, and then it got to there. Now, some of it would go this way, and the rest would go this way, and then it would join up, and then it would be part of the main part again. There we go. So I feel like doing something over here. So if we'll say that the yellow part, you don't have to do this in your exam, this is just me teaching you guys. That is part of the main circuit. We'll call this branch 1 of the parallel. And this is branch 2 of the parallel. So so what I'm going to show you now is that in the blue, can you see that we've got all of these? So they are in series within the blue, okay? Within the blue, they are in series. So we are going to work out the blue. So let's go work out the blue. So because it's in series, we can just add them up. So the R will be equal to, or the resistance will be equal to R plus 2R plus 3R, and that's going to be equal to 6R. Now, we know that 6R, which is the total of this branch, that is now in parallel with this one over here. So now we can use the parallel formula. So we know that the parallel formula goes like this. 1 over R parallel is equal to 1 over R of the first branch, so branch 1, plus 1 over R of branch number 2. Right, now what we can go and do is we're just going to go fill in branch 1, which is 6R, not 6 ohms, hey? It's 6R, it's an unknown. And branch 2 that's just a single one, so that's just going to be 4R. And then the R parallel, we also know that is 4.8, so we can say 4.8. We don't have to say R for that, because they've actually given us the value. And so we can do this in multiple different ways. You can get a common denominator right now. So what I'm going to quickly do is I'm just going to type this on my calculator so it can turn it into a fraction. And what it does is it turns it into 5 over 24. So now I can get a common denominator. I can see that my common denominator will be 24R. 24R. That would be the common denominator. So I'm going to have to multiply this one by R, and what you do to the bottom, you do to the top. I'm going to multiply this one by 4, because what you do to the bottom, you do to the top, and I'm going to multiply this one by 6. What you do to the bottom, you do to the top. And so what we're going to end up with now is 5R over 24R equals to 4 over 24R plus 6 over 24R. Now, because the denominators are the same, we can ignore them. Okay, so I'm going to take them out. And then we can go and solve. So we're going to end up with 5R is equal to 10. And so therefore R is equal to 2 ohms. Now, because R is equal to 2 ohms, we can now go fill in all of these values. I'll do that on the next slide, but we now have R, so we can go fill in all of those. Right, so now we already worked out R as 2, so this means that this will be 8 ohms, this will be 2 ohms, this will be 4 ohms, and this would be 6 ohms. Now it says calculate the reading on the voltmeter if the current through the 4 ohm resistor is 1.8. Okay, but now we need to see what the 4R was. Which one was that? That one was, oh, that one was this one. Oh, okay. Okay, and I forgot to add the marker location, but there it is. This one's worth 5 marks. Can I tell you a really random, stupid story? But I've always wondered, I don't know, when we talk about marks, like imagine your name is Mark. Like there's a lot of marks. Like I know, like literally in the little estate that I live in, there's probably like 5 marks. So like, imagine every time the teacher talks about how many marks you got. Like just, I know it sounds stupid, but just think about it. Let's imagine your name is Martin, okay? Just think about this. Now your teacher's like, oh, you got 37 Martins out of 50 Martins. Or you got 12 Martins out of 13 Martins. Or hey bro, how many Martins did you get? You know, listen carefully to what I'm saying. Like these poor people mark. Like we say, hey, how many marks did you get? Or what's the test out of? Oh, it's out of 150 marks. It's weird, right? Like if you think about it, I hope that you're never going to look at the word Mark ever again, and you're going to have a respect for people who are named Mark, because these poor people, like we talk about them as if they, like we're not showing the respect. Like, hey bro, how many marks you got? Bro, that's my name. Okay, that was probably the most random side topic conversation I've ever had. Sure, interesting. So as we were saying, 5 marks. Okay, so or like yeah, I think I should stop. So like whatever your name is, put your name in the place of Mark and imagine that's what people did, because that's how people who are called Mark feel. Like let's say your name's Tabo. Like, hey bro, how many Tabos did you get? You see, now it sounds weird, right? But when we say Mark, everyone's like, oh no, it's fine. Oh, Kevin. How many Kevins did you get? I got 4 Kevins out of 5. Okay, yeah, I think I'm going to stop there. So, calculate the reading on the voltmeter if the current through the 4 ohm resistor is 1.8 amps. When you laugh at your own jokes. Okay, wait, one more. Imagine your name is Penelope. So, hey bro, how many Penelopes did you get? This test out of 15 Penelopes. It's weird, right? Just one more thing. I mean, language is just weird. Like, I'm sitting right now at a table. Like, who was the person who called this a table? Like, this desk that I'm sitting at right now, it literally could have been called a dog. And the dog that I really have in my house, that could have been called a table. And I could have been like, oh, here comes my cute, beautiful table. And now I'm busy sitting at my dog. You know, we would never know the difference. Do you know what I mean? Like, we wouldn't know that that's wrong. Or like, wow, I'm busy writing with my windows at the moment. And I'm busy looking out my pen. You see, like, the words we use, they only make sense because we're so used to them. But we never invented them. But they become so normal for us. And that's so weird if you think about it. Hey? Okay, so let's really carry on now. So I'm going to quickly go get a highlighter. And I'm going to highlight what we did in the previous question. So the blue was the lower branch and the green was the upper branch. I'm not sure if we're going to need to use that, but let's just do it anyways. And then this we said was part of the main branch. Okay, I'm not sure. As I said, I'm not sure we're going to need to use that, but let's just see. So it says, calculate the reading on the voltmeter if the current through the 4R. Now, don't say 4 ohm. They're not talking about that one. Okay, we're not going to write in yellow. That's not going to work out so nicely. If the current through the 4R, which is this one, they're saying that reading is 1.8 amps. So this one's actually not too bad, because what we can do now is just using these two, this resistor and this current, we know that we can calculate the voltage. So we know that there's this formula I equals to V over R, and if we had to rearrange it to get V by itself, it would say V equals to I times R, or let's write it the normal way around, V equals to IR. And so the voltage is going to be equal to 8 multiplied by 1.8, and that's going to give us 14.4 volts. Okay, so now we know the voltage across this one over here. Okay, so we can go fill this in over here. So that one there is now 14.4 volts. Now, what do we know about parallel branches? What do we know about the voltages? Given the voltages are the same in parallel. That's correct. Nice. So the total voltage for the branches are the same. So we can say parallel branches have the same voltage. But what does that now mean? Does it mean that all of these are going to be 14.4 volts? Like, does that mean each one is going to be 14.4? No. It means that the total branch is going to be 14.4. So the total branch will be 14.4 volts. So that means that the voltage of the 3R resistor, or let's say the 6 ohm resistor, plus the voltage of the 4 ohms, that's 4 ohms, plus the voltage of the 2 ohm should add up to 14.4. So what we could do now is we could just go use the IR formula for each of these. So we could use the I times by the 6 ohm resistor. Now what I is this? Well, this will be the I, the current that is flowing through this blue half. Okay, so we don't know what that is, so we'll just say I times 6 plus I times 4 plus I times 2 should be 14.4. If we then add all of these together, we should end up with 12I equals to 14.4. And if you had to work out the current, you're going to get 1.2 amps. Where's that 1.2 amps? That is the 1.2 amps that is flowing through this part over here. So we know that going through here, there's 1.2 amps. Whoa, Kevin, that's ohms, buddy. And so now, if I look at this part over here, I could calculate the voltage by using I times R, because I now know the current flowing through there, it's 1.2, and I know the resistance, which is 4, and if I had to go work that out, I get 4.8 volts. The next question, I just wanted to also remind you though that this question does still carry on the next slide. So it says here, calculate the energy, so that's not power, hey? That's energy. There's a difference between power and energy converted in the 4R in 2 minutes. So that's this one in 2 minutes. And this one is for 3 marks. So what I want you to remember, and I'll obviously go get the formal and the proper formulas now, but please remember that power is the energy divided by time. So if you wanted to get energy by itself, you could say that energy is power multiplied by time. And power can be calculated in multiple different ways. You know, there's the formula P equals to VI, P equals to I squared times R, P equals to V squared over R. So you can then go find out whichever one of these you can, and then you can substitute that over here. Okay, now I'm going to show you what the formula sheet looks like. So now you see on the formula sheet they'll give you these 3, but all that they're actually doing is they're just replacing the power with VI for this one, and they're calling W the energy, okay? And then they're replacing I squared times R in the power's place, and then V squared over R they're using. So that's really what's happening there. So you can choose whichever one you like. But obviously there is a nice way to choose, like choose whatever you have. So it says calculate the energy in the 4R, so that's this one. Okay, so we have the resistance, we have the current, but we also have the voltage. I think we also worked out the voltage as 14.4 volts. So you could really choose any one of these formulas. They would all work. I'm just going to be very boring, and I'm just going to choose the first one. And so I'm going to say W is equal to the voltage, which we worked out there was 14.4, multiplied by the current in that part, which is 1.8, multiplied by the seconds. Remember, the time must be in seconds. That would be 120. And if you had to go work this out, you end up with 3110.4 joules. Okay? Now, if any of you are like, Kevin, my bro, I'm so confused because I thought power is W. Ha! I know what you mean. But what that means is that power, when you give your answer for power, the units are in W, like 10 watts. But this is the symbol. Okay? So the unit of power, like when you actually give your answer, is in watts. But the symbol of energy is W. Okay? So it is a bit weird. I know. Okay, here's our next, or our last part. So it says the 4R resistor is replaced with an ammeter. Okay, so we're going to take this one out Okay, and we're rather going to put an ammeter there. Now an ammeter has no resistance, negligible resistance actually. So we've taken this resistor out. So this branch has no resistance right now. So that's been taken out. How will the reading on this voltmeter be influenced? Right, only increase, decrease, or stays the same? Okay, so what we got to understand is I want you to pretend that you are an electron right now, okay? You an electron, right? It's the 21st century. You can be an electron if you want to, bro. Like if you want to be an electron in the like if you want to go to your grandparents this afternoon or this evening and be like, guys, from now on you will call me an electron. You can do that. So when I say pretend you're an electron, yeah, you can take me serious if you really want to. So you are an electron. Now what happens is that when that electron flows down here, when that electron gets here, it needs to make the decision whether it's going to pop a right, like a little right turn over there. Some of you might say, Kevin, that's left. But if you are the electron, then you're driving this way, right? So you'd actually be making a right-hand turn. Okay, that's not that important. So you'd make a right-hand turn and you'd go down this way. Or you could decide to go this way. Now, you're an electron, so you are looking for the easiest pathway. You're not looking for a difficult pathway. You're not a 4x4 electron. You just want to chill on the highway. That's the way electrons work. They want to find the easy path. So, would the electron decide to go through this path, which has pretty much no resistance, or would it decide to go 4x4ing through all of these resistors over here? Well, the electron would go this way because it chooses the path of less resistance, or in fact there is no resistance in that path, so all the electrons are going to go that way. Not even one electron would go this way. What that then means is that the amount of current flowing, or the amount of electrons going through this part here, would be 0. So this voltmeter reading would actually go all the way down to 0 volts. So we are going to say here decrease. So we could almost say, well, we can say that this has created some type of short circuit. Okay, so now for 12.5, explain your answer. We'll just say that no current will flow through the 2R resistor.